You're standing in a room that has no walls, no ceiling, no floor. You walk forward, searching for the boundary, but there is no edge to find. The room is not infinite, it simply refuses to end. This is not a riddle, it is the universe. We live inside something expanding faster than light itself, and yet there is nothing for it to expand into. Scientists confirmed this decades ago, and most of humanity still struggles to picture it. The human mind craves borders, horizons, a place where something stops and something else begins. But the cosmos does not obey that instinct. The universe is not pushing into a void. There is no outer darkness waiting to be filled. Space itself is the thing growing, stretching, multiplying. If you are ready to see how this paradox dismantles everything you thought you knew about reality, hit that like button and subscribe. Tell me in the comments, do you think the universe has an edge, or does it stretch forever? Now settle in, relax, and let the journey begin. The problem begins with language. When you hear the word expansion, your brain conjures an image of something spreading outward, like ink bleeding into water or a city sprawling into the countryside. But the universe is not a city. It is not an object moving through space. It is space. Imagine a balloon with dots painted on its surface. As you blow air into the balloon, the dots move farther apart. But here is the critical detail. The dots are not sliding across the rubber. The rubber itself is stretching, carrying them along. There is no external room the balloon is inflating into. The surface of the balloon is all there is. This is the Raisin Bread cosmos, the metaphor that physicists used to explain what Edwin Hubble discovered in 1929. Galaxies are not flying through space like ships across an ocean. Space is the ocean, and it is deepening, widening, multiplying between them. The farther two galaxies are from each other, the more space there is between them to expand, which is why distant galaxies appear to recede faster than nearby ones. But the question remains, stubborn and unsettling. If space is expanding, what is it expanding into? The answer is nothing. Not a void, not a vacuum, not an empty room waiting to be filled. Nothing. The confusion arises because we are creatures of edges. We grow up in a world of walls and horizons. Every object we encounter has an inside and an outside, a beginning and an end. We cannot help but project that structure onto the universe. But the cosmos does not care what our minds can picture. It simply is. The universe does not need a container. It is not embedded in anything. When cosmologists say the universe is expanding, they mean that the metric of space-time itself is growing. Distance is not a fixed thing. It is a relationship, and that relationship is changing. A galaxy 1 billion light-years away today will be farther tomorrow, not because it moved, but because the space between here and there grew. This is not a new idea. In 1922, a Russian physicist named Alexander Friedmann solved Einstein's equations and discovered that a static universe is impossible. The fabric of space-time cannot sit still. It must either expand or contract. Einstein himself resisted this conclusion, adding a fudge factor called the cosmological constant to hold the universe in place. He later called it his greatest blunder. But Friedmann was right. And 7 years later, Hubble proved it. He measured the light from distant galaxies and found that it was stretched, shifted toward the red end of the spectrum. The farther the galaxy, the more the light was stretched. This was not because the galaxies were moving, it was because the space the light travelled through had expanded while the light was in transit. This discovery shattered the ancient illusion of a static, eternal cosmos. The universe had a history. It had been smaller yesterday, denser last year, unimaginably compact billions of years ago. And if you run the clock backward far enough, you arrive at a moment when all of space was compressed into a point smaller than an atom. This is the Big Bang, not an explosion in space, but an explosion of space. And that is where the illusion of edges collapses entirely. Because if the universe began as a single point, there was no outside for it to expand into. There was no stage, no backdrop, no pre-existing void. The point was not sitting in some larger arena. It was the arena, all of it. The universe does not expand into anything. It expands as everything. The universe does not behave like a city sprawling into farmland. It behaves like dough rising in an oven. Picture a loaf of raisin bread before it is baked. The dough is dense, compact, studded with raisins spaced evenly throughout. Now slide it into the oven. As the heat works through the dough, the entire loaf begins to swell. The raisins do not move through the dough. They are carried apart by the dough itself as it expands. A raisin near the edge of the loaf does not travel farther than one in the center. Every raisin sees every other raisin moving away. There is no center to the expansion. There is no edge. This is the universe. The dough is space, the raisins are galaxies, and the oven is time. When Edwin Hubble aimed his telescope at distant galaxies in 1929, he did not find objects flying through a static void. He found something stranger. The galaxies were receding, yes, but the farther away they were, the faster they appeared to move. A galaxy twice as distant was moving away twice as fast. One 3 times farther was fleeing 3 times faster. This was not the signature of an explosion scattering debris. It was the signature of space itself stretching. Hubble measured this by studying light. Light from distant galaxies was not the colour it should have been. It was redder, stretched toward the crimson end of the spectrum. This phenomenon, called redshift, occurs when the source of light is moving away from the observer. But the galaxies were not racing through space like ships through water. The space between us and them was expanding, stretching the light waves as they travelled. By the time the light reached Earth, it had been pulled thin, its wavelength elongated. This discovery shattered the assumption of a static cosmos. For millennia, humans had imagined the universe as eternal and unchanging, a stage upon which events unfolded but which itself never moved. Hubble's observations proved otherwise. The universe had a history. It was smaller yesterday, denser last year, impossibly compact billions of years ago. Albert Einstein had already given humanity the tools to understand this, though he resisted the conclusion for years. In 1915, he published his theory of general relativity, a radical reimagining of gravity not as a force, but as a curvature of space-time. Mass and energy warp the fabric of the cosmos like a bowling ball sinking into a trampoline. Objects do not fall toward each other because of some invisible tug. They follow the curves that massive objects carve into space-time. But Einstein's equations also revealed something he found deeply unsettling. The universe described by his mathematics could not stand still. It had to be either expanding or contracting. Faced with this prediction, Einstein added a term to his equations, a mathematical fudge factor called the cosmological constant, designed to hold the universe in place. He called it his greatest blunder. Because the universe does not hold still. In 1922, a Russian physicist named Alexander Friedmann solved Einstein's original equations without the cosmological constant, and found that the universe must be dynamic. It could expand, contract, or oscillate, but it could never remain static. Einstein dismissed Friedmann's work. 5 years later, a Belgian priest and astronomer named Georges Lemaitre reached the same conclusion and even found observational evidence to support it. Einstein again resisted. Then Hubble's data arrived, irrefutable and relentless. The universe was expanding. By 1931, Einstein had abandoned his static model and embraced the reality his own equations had predicted. The cosmos was not a stage, it was a story. But this raised a question that still haunts human intuition. If the universe is expanding, what is it expanding into? The question assumes there is some pre-existing void, some larger container into which the universe is growing. But general relativity does not describe the universe as an object embedded in space. It describes the universe as space itself. Space is not a thing that exists inside something else. It is the framework within which existence unfolds. When cosmologists say the universe is expanding, they mean the metric of space-time is changing. Distance is not a fixed property. It is a relationship, and that relationship is growing. A galaxy that is 1 billion light-years away today will be farther tomorrow, not because it moved through space, but because the space between here and there multiplied. This is metric expansion, the stretching of the cosmic fabric. It is not galaxies moving, it is the stage itself growing larger, carrying everything with it. And because space-time is all there is nothing for it to expand into. The question dissolves. The universe is not expanding into anything, it is simply becoming more. The question haunts us because we are built wrong for the answer. Every human brain is wired to think in terms of containers. A cup holds water, A room contains furniture, a city sprawls into countryside. We cannot help but imagine the universe as an object sitting inside something larger, expanding into some pre-existing void. But this is not how reality works. The universe is not a thing in a place, it is the place. When cosmologists say the universe is expanding, they do not mean it is pushing into empty space. They mean the fabric of space-time itself is stretching. Distance is not fixed, it is a relationship, and that relationship is growing. A galaxy 1 billion light-years away today will be farther tomorrow, not because it moved, but because the space between here and there multiplied. This is not speculation. It is observed fact, confirmed by multiple independent lines of evidence spanning nearly a century. Edwin Hubble's 1929 discovery that distant galaxies are receding was only the beginning. Since then, astronomers have measured the expansion using supernova, cosmic microwave background radiation, gravitational lensing, and the large-scale structure of the universe. Every method points to the same conclusion: space is growing. The most direct evidence comes from redshift. Light from distant galaxies is stretched, shifted toward the red end of the spectrum. The farther the galaxy, the more the light is stretched. This is not because the galaxies are flying through space like bullets. It is because the light travelled through expanding space, and the expansion stretched the wavelengths. By the time the light reaches Earth, it has been pulled thin, its colour shifted. In 1998, two teams of astronomers studying distant supernovae made a discovery that shocked the physics community. They found that the universe is not just expanding, it is accelerating. The expansion rate is increasing over time. Distant supernovae appeared dimmer than expected, meaning they were farther away than they should have been in a universe expanding at a steady rate. Something was pushing the cosmos apart faster and faster. This discovery earned a Nobel Prize and introduced a new mystery: dark energy. Roughly 68% of the universe is composed of this invisible force, and we have no idea what it is. It does not emit light. It does not interact with matter. It simply pushes, driving galaxies apart, accelerating the expansion. More evidence arrived from the cosmic microwave background, the faint radiation left over from the Big Bang. This light, now stretched into microwaves, fills the entire universe. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory measured tiny temperature fluctuations in this radiation, revealing a snapshot of the universe as it appeared 380,000 years after its birth. The pattern of these fluctuations matches the predictions of an expanding universe. The cosmos was once much smaller and denser, and it has been stretching ever since. Gravitational lensing provides yet another confirmation. Massive objects like galaxy clusters warp space-time, bending the light from more distant galaxies. By studying how this light is distorted, astronomers can measure how the universe has expanded over billions of years. The data matches the predictions of an accelerating expansion. Even the distribution of galaxies across the cosmos tells the same story. Galaxies are not scattered randomly. They form a web of filaments and voids, a structure shaped by gravity over billions of years. The pattern of this cosmic web depends on the expansion history of the universe. Observations match the predictions of a universe that has been expanding since the Big Bang and is now accelerating. The James Webb Space Telescope recently provided the most precise measurements yet, confirming earlier results from the Hubble Space Telescope. Using multiple methods to measure cosmic distances, Webb found that the universe is expanding at a rate of about 72.6 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space is stretching by 72.6 kilometers every second. The measurement is accurate to within 2%. But here is the twist. When astronomers calculate what the expansion rate should be based on the early universe, they get a different number. The cosmic microwave background predicts an expansion rate of about 67 kilometers per second per megaparsec. The discrepancy is known as the Hubble tension, and it remains one of the biggest unsolved problems in cosmology. The tension suggests that something is missing from our understanding. Perhaps dark energy is not constant. Perhaps the universe expanded differently in the past. Perhaps there is some feature of the cosmos we have not yet discovered. The answer will rewrite cosmology. But the core fact remains unshaken. The universe is expanding. Space itself is stretching, and there is nothing for it to expand into because space is not a container. It is the totality of existence. The question, what is the universe expanding into, is the wrong question. It assumes a framework that does not apply. The universe is not expanding into anything. It is simply becoming more. In 1922, a Russian physicist named Alexander Friedmann solved a problem that Albert Einstein refused to acknowledge. Friedmann took Einstein's equations of general relativity and applied them to the universe as a whole. He made two simplifying assumptions. First, that the universe looks roughly the same in every direction. Second, that it looks roughly the same from every location. These assumptions, known as the cosmological principle, allowed him to simplify the mathematics. What he found was unsettling. The universe could not stand still. Einstein's equations described spacetime as a dynamic fabric, warped and shaped by mass and energy. But when applied to the cosmos at large, the mathematics revealed something inescapable. A static universe was impossible. The fabric of space had to be either expanding or contracting. There was no middle ground. Gravity pulled everything together, and unless something pushed back, the universe would collapse. Friedmann's solution showed three possibilities. The universe could expand forever, slowing down but never stopping. It could expand, reach a maximum size, and then collapse back on itself. Or it could balance perfectly on the edge between the two, expanding at a rate that gradually approaches zero. All three scenarios involved change. None allowed for stillness. Einstein hated this conclusion. At the time, every observation suggested the universe was eternal and unchanging. Galaxies existed, stars burned, but the cosmos itself seemed fixed. The idea that the entire universe could be expanding or contracting struck Einstein as absurd. So in 1917, 5 years before Friedmann's work, Einstein had added a term to his own equations. He called it the cosmological constant, represented by the Greek letter lambda. The cosmological constant acted like a repulsive force, a kind of anti-gravity that pushed space apart. Einstein tuned it to exactly balance the attractive force of gravity, creating a universe that neither expanded nor collapsed. It was a delicate equilibrium, a cosmic tightrope, but it allowed the universe to remain static, which is what Einstein believed the data demanded. Friedmann's equations showed that this equilibrium was a mirage. The static solution was unstable. If the universe expanded even slightly, the expansion would release energy, causing more expansion. If it contracted even slightly, gravity would pull it into collapse. The universe could not balance on that edge. It would tip one way or the other. Einstein dismissed Friedmann's work at first, claiming there was a mathematical error. Friedmann wrote back, politely pointing out that the equations were correct. Einstein checked again and published a retraction, acknowledging that Friedmann's mathematics was sound. But he did not embrace the conclusion. He still believed the universe was static. Then, in 1927, a Belgian priest and astronomer named Georges Lemaitre independently derived the same solution. Lemaitre went further. He argued that if the universe was expanding now, it must have been smaller in the past. Running the clock backward, he proposed that the entire cosmos had originated from what he called a primeval atom, a single point of unimaginable density. This was the seed of what would later be called the Big Bang. Lemaitre even found observational evidence. He noticed that the light from distant galaxies was redshifted, stretched toward the red end of the spectrum. This suggested the galaxies were moving away, exactly as an expanding universe would predict. He presented this evidence to Einstein in person. Einstein reportedly replied that while the mathematics were correct, the physics was abominable. 2 years later, Edwin Hubble published his landmark observations. Using the most powerful telescope of the era, he measured the distances to dozens of galaxies and found that nearly all of them were receding. The farther they were, the faster they appeared to move. The relationship was linear, exactly as Friedmann and Lemaitre had predicted. The universe was expanding. Einstein accepted defeat. By 1931, he had abandoned the cosmological constant and embraced the expanding universe. He called the cosmological constant his greatest blunder. But the story did not end there. In 1998, astronomers studying distant supernovae discovered that the expansion of the universe is accelerating. Some force is pushing galaxies apart faster and faster. The simplest explanation is a cosmological constant, a repulsive energy woven into the fabric of space itself. Einstein's blunder had returned, not as a tool to hold the universe still, but as the dominant force shaping its future. Today, the cosmological constant is understood as dark energy, a mysterious component that makes up 68% of the universe. It is the reason space is expanding and the reason that expansion is speeding up. Friedmann's equations, once dismissed, are now the foundation of modern cosmology. They describe a universe that refuses to be static, a cosmos that is always becoming. 1929 was the year the universe gained a history. Edwin Hubble stood at the eyepiece of the Hooker telescope on Mount Wilson, California, the most powerful instrument on Earth at the time. Its 100-inch mirror could resolve galaxies millions of light-years away, pulling faint spirals and ellipses out of the cosmic dark. Hubble was hunting distances, trying to measure how far these island universes truly were. What he found rewrote everything. He focused on a specific type of star called a Cepheid variable. These stars pulse with clockwork regularity, brightening and dimming over days or weeks. The period of the pulse is tied to the star's intrinsic brightness. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. By measuring the period, astronomers could calculate how bright the star truly was. By comparing that to how bright it appeared from Earth, they could calculate its distance. Hubble found Cepheids in dozens of galaxies. He measured their distances. Then he did something unexpected. He studied the light from those galaxies and noticed it was wrong. The spectral lines, the fingerprints of specific atoms, were shifted toward the red end of the spectrum. The farther the galaxy, the more the light was shifted. This was redshift, and it meant the galaxies were receding. But the pattern was even stranger. The relationship was linear. A galaxy twice as far was receding twice as fast. One 3 times farther was moving away 3 times faster. This was not the signature of an explosion scattering debris. It was the signature of space itself stretching. Hubble plotted the data. Distance on one axis, velocity on the other. The points fell along a straight line. The slope of that line became known as the Hubble constant, a number that describes how fast the universe is expanding. Today, nearly a century later, that number remains one of the most important measurements in cosmology. It determines the age of the universe, the fate of the cosmos, and whether our understanding of physics is complete. But measuring the Hubble constant has become one of the most contentious problems in modern science. There are 2 primary ways to measure the expansion rate. The first uses the local universe. Astronomers observe nearby galaxies, measure their distances using Cepheids and supernovae, and calculate how fast they are receding. This method, led by the Suez collaboration using the Hubble Space Telescope, and now the James Webb Space Telescope, gives a value of around 73 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space is stretching by 73 kilometers every second. The second method uses the early universe. Satellites like the Planck Observatory measured the cosmic microwave background, the faint radiation left over from the Big Bang. By studying tiny temperature fluctuations in this ancient light, cosmologists can calculate what the expansion rate should be today. This method gives a value of around 67 kilometers per second per megaparsec. The difference is small, only about 9%, but the measurements are precise. The error bars no longer overlap. By some estimates, the discrepancy has grown to more than 5 sigma, meaning there is less than a 1 in a million chance this is a statistical fluke. This is the Hubble tension, and it has become a crisis. At a meeting of the American Astronomical Society in January 2025, astronomer Dan Skolnick declared that the tension was no longer a puzzle. It was a crisis demanding resolution. By September 2025, at the Tensions in Cosmology conference in Corfu, Greece, the tension had reportedly exceeded 6 sigma. Multiple independent methods, including gravitational lensing time delays and maser measurements, all confirmed the higher value. Some researchers argue the tension may be resolved by refining measurements. A 2025 study using the tip of the red giant branch method, which measures distances using the brightest red giant stars, found a middle value of 70.4 kilometers per second per megaparsec. The error bars of this measurement overlap with both the early and late universe values, suggesting the tension might be a measurement issue rather than a sign of new physics. But most cosmologists are not convinced. The TD-Cosmo collaboration, which uses gravitationally lensed quasars to measure the expansion rate, found a value of 72.1 kilometers per second per megaparsec, strongly supporting the higher measurement. This method is entirely independent of Cepheids and supernovae, yet it arrives at the same answer. The tension suggests something is missing from our understanding. Perhaps dark energy is not constant. Perhaps the early universe expanded differently than the standard model predicts. Perhaps some new particle or force altered the fabric of space-time in ways we have not yet discovered. Solutions under consideration include early dark energy, modifications to gravity, and changes to the physics of cosmic recombination. The next few years will be critical. New data from the James Webb Space Telescope, the Atacama Cosmology Telescope, the Simons Observatory, and the Dark Energy Spectroscopic Instrument will either resolve the tension or confirm that the standard model of cosmology is incomplete. Hubble's 1929 discovery gave the universe a history. The tension that bears his name may give it a future we cannot yet imagine. The universe began, not in a place, not at a time. It began as the creation of place and time themselves. This is the Big Bang, the moment when everything that exists erupted from a state of unimaginable density and heat. It was not an explosion in space, it was an explosion of space. There was no stage, no backdrop, no pre-existing void into which the universe expanded. The singularity was not sitting somewhere, it was everywhere. All of space, all of time, compressed into a single point smaller than an atom. For decades, this idea was dismissed as absurd. Then, in 1964, two radio astronomers accidentally proved it true. Arno Penzias and Robert Wilson were working at Bell Labs in Holmdel, New Jersey, with a massive horn-shaped antenna originally built for satellite communications. They were hunting for radio signals from the Milky Way, mapping the faint whispers of radiation between the stars, but they kept detecting noise, a persistent hiss that would not go away. They checked everything. They thought it might be interference from New York City, 40 miles away. They ruled that out. They thought it might be radiation from nuclear tests. They ruled that out too. They even found a pair of pigeons nesting inside the antenna and cleaned out what they politely called a white dielectric material. The noise remained. The hiss was coming from the sky itself. It was the same in every direction, day and night, summer and winter, unchanging. 60 miles away at Princeton University, a team of astrophysicists led by Robert Dicke had been preparing to search for exactly this signal. They had calculated that if the universe began in a hot, dense state, it should have released a tremendous burst of radiation. Over billions of years, as space expanded and cooled, that radiation would have stretched into microwaves. It should still be detectable, filling the entire universe with a faint glow. Penzias called Dicke. Dicke listened to the description of the noise, hung up and turned to his colleagues. "Boys, we've been scooped," he said. The radiation Penzias and Wilson had detected was not noise. It was the cosmic microwave background, the oldest light in the universe, a photograph of the cosmos as it appeared 380,000 years after the Big Bang. Before that moment, the universe was so hot that atoms could not form. Electrons and protons flew free, colliding endlessly with photons of light. The cosmos was opaque, a churning fog of energy. Then, as space expanded and cooled, the temperature dropped below 3000 Kelvin. Electrons and protons combined to form the first hydrogen atoms. Light was finally free to travel. That light has been travelling ever since. It has stretched with the expansion of space, cooling from visible light to infrared to microwaves. Today, 13.8 billion years later, it fills the universe with a temperature of 2.725 Kelvin, just 3 degrees above absolute zero. This discovery transformed cosmology. For the first time, scientists had direct evidence that the universe was once far hotter and denser than it is today. The Big Bang was no longer a speculative idea, it was an observed fact. Penzias and Wilson won the Nobel Prize in 1978. But the cosmic microwave background revealed more than just the existence of the Big Bang. It revealed the structure of the early universe. In 1992, the Cosmic Background Explorer satellite COBE detected tiny temperature fluctuations in the radiation. Some regions were slightly warmer, others slightly cooler. The variations were minuscule, only a few parts in 100,000, but they were real. These fluctuations were the seeds of everything that exists today. The slightly denser regions collapsed under gravity, pulling in matter and forming the first stars, galaxies, and galaxy clusters. The slightly less dense regions became the voids, the great empty spaces between the cosmic web. The pattern of these fluctuations matches the predictions of inflation, the theory that the universe underwent a brief period of exponential expansion in its first fraction of a second. Subsequent missions refined the picture. The Wilkinson Microwave Anisotropy Probe, WMAP, mapped the fluctuations in unprecedented detail. The Planck satellite pushed the precision even further, measuring the age of the universe, the density of matter, and the expansion rate with extraordinary accuracy. But the cosmic microwave background also poses a profound mystery. The temperature is the same in all directions to within 1 part in 100,000. Regions of the sky separated by vast distances, so far apart that light could not have travelled between them in the time since the Big Bang, have exactly the same temperature. How did they come to equilibrium? This is the horizon problem, and it suggests that something happened in the earliest moments of the universe that brought distant regions into contact. Inflation solves this problem by proposing that space itself expanded faster than light, carrying regions that were once close together to opposite sides of the observable universe. The cosmic microwave background is the strongest evidence for this idea. The Big Bang singularity is not a point in space, it is the beginning of space. It is the moment when distance, time, and causality emerge from a state that physics cannot yet fully describe. The cosmic microwave background is the echo of that moment, a faint whisper from the edge of time itself. Space is not empty. It is not nothing. It is a thing, a substance, a medium that bends and stretches and ripples like the surface of an ocean. This is the insight Albert Einstein gave humanity in 1915 with his theory of general relativity. Before Einstein, space was thought to be an unchanging stage, a fixed backdrop against which events unfolded. Time was absolute, ticking forward at the same rate everywhere in the universe. But Einstein showed that space and time are woven together into a single fabric called space-time, and that fabric is dynamic. It warps in the presence of mass and energy. It curves around stars and planets. It ripples when black holes collide, and it stretches as the universe expands. The classic metaphor is a rubber sheet. Place a bowling ball on the sheet and it creates a depression, a well in the fabric. A marble rolled nearby will curve toward the bowling ball, not because some invisible force is pulling it, but because the sheet itself is warped. This is gravity. Objects do not fall toward each other because of some mysterious attraction. They follow the curves that mass carves into space-time. But space-time is more than just bendable. It is stretchable. And in the earliest moments of the universe, it stretched faster than anything physics had ever predicted. This is cosmic inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. The universe began unimaginably small, perhaps as tiny as 1024 centimeters, 100 billion times smaller than a proton. Then, in less than 10 to 35 seconds, it exploded in size. Space doubled every 10 to 37 seconds. By the time inflation ended, the universe had grown by a factor of at least 10 to 26. A region smaller than an atom had ballooned to the size of a grapefruit and possibly much larger. This sounds impossible. Nothing can travel faster than light. But inflation does not violate relativity, because it is not objects moving through space, it is space itself expanding. Points in space-time were not racing away from each other. The distance between them was simply multiplying. Physicist Alan Guth proposed the theory in 1980 to solve several deep problems with the Big Bang model. The first was the flatness problem. The universe appears to be geometrically flat, meaning parallel lines remain parallel even across cosmic distances. But for the universe to be flat today, its initial density had to be tuned to an almost impossible precision, accurate to within 1 part in 10^1060. Any deviation would have caused the universe to either collapse or fly apart long ago. Inflation solves this by stretching space so rapidly that any initial curvature was flattened out, like pulling a wrinkled sheet taut. The second problem was the horizon problem. The cosmic microwave background has the same temperature in all directions to within 1 part in 100,000, but regions of the sky separated by more than a few degrees were never in causal contact. Light could not have travelled between them in the time since the Big Bang. How did they come to equilibrium? Inflation solves this by proposing that all the regions we see today were once close enough to reach the same temperature before inflation blew them apart. The third problem was the magnetic monopole problem. Grand unified theories of particle physics predict that the early universe should have produced massive magnetic monopoles, particles with only a north or south pole. These monopoles should be everywhere, but none have ever been found. Inflation solves this by diluting them. If monopoles formed before inflation, they would have been spread so thin by the expansion that the chances of finding one are nearly zero. But inflation's most profound consequence is that it explains where structure came from. The galaxies, the stars, the planets, everything that exists today originated from quantum fluctuations during inflation. In the earliest moments, space was not perfectly smooth. Tiny variations in energy density governed by the uncertainty principle flickered in and out of existence. Inflation stretched these microscopic fluctuations to cosmic scales, freezing them into the fabric of space. When inflation ended, these variations became the seeds of structure. Gravity amplified them over billions of years, pulling matter into the first stars, galaxies, and galaxy clusters. The evidence for inflation is written in the cosmic microwave background. The pattern of temperature fluctuations matches the predictions of quantum fluctuations stretched by exponential expansion. The data from satellites like WMAP and Planck confirm that the universe is flat, that distant regions were once in contact, and that the seeds of structure have precisely the properties inflation predicts. Inflation was driven by a field called the inflaton, a form of energy that filled all of space. This field had a strange property, negative pressure. While normal matter and energy pull things together through gravity, the inflaton pushed space apart. As the inflaton field decayed, it released its energy into particles, light, and matter, reheating the universe and beginning the hot Big Bang phase that Hubble and Penzias observed. The theory remains incomplete. Cosmologists do not yet know what the inflaton field was, what caused it to exist, or what came before inflation. But the framework has become indispensable. It transforms the Big Bang from a singularity, where physics breaks down, into a quantum event where space itself was born, stretched, and seeded with the structure that would one day become us. Imagine a siren racing away from you through a dense fog. As it speeds off, the pitch of the sound drops, the familiar Doppler effect. Waves stretch, frequencies fall, the howl becomes an echo. Light too has its sirens, and as galaxies rush away, their light is stretched by the same relentless law. This cosmic stretching is called redshift, and it is the universe's most persistent clue, evidence stamped on every photon that space itself is growing. But the redshift is not just about motion, it is about expansion. When astronomers observe distant galaxies, they see their light shifted toward the red end of the spectrum. The farther away the galaxy, the redder its light. At first, you might picture these galaxies as ships sailing through an ocean, fleeing some central point. But there is no ocean. There is no center. The galaxies are not moving through space. It is space itself that is growing, stretching the light as it travels. Every photon that leaves a distant star begins its journey with a signature, a precise color, a crisp frequency. As the photon travels, space expands beneath its feet. The very fabric of the cosmos stretches, pulling the light's wavelength wider and wider. By the time that ancient photon meets your telescope, its color has shifted, reddened by the journey. Lyman alpha becomes H alpha, ultraviolet melts into infrared. The message is clear. Space grew while the light was in flight. The entire story of the universe's expansion is inscribed in this stretching. In 1929, Edwin Hubble plotted redshifts against distances and discovered, the farther the galaxy, the greater its redshift. This linear relationship, now called Hubble's law, is the proof that all of space is stretching, not just the stuff within it moving. It is the difference between raisins moving apart inside swelling dough and marbles rolling away on a playground. The dough, the fabric, is changing. There is no outside for it to move into. But why does redshift matter? Because it is not a shadow or afterimage. It is a measurement a yardstick for the cosmos. By measuring redshifts, astronomers can trace the expansion of space itself back to the very first moments after the Big Bang. Patterns in the cosmic microwave background, the oldest light in existence, reveal the same expansion, the same relentless stretching. The temperature ripples in that ancient light are fingerprints of a universe eternally in motion. None of this would be possible without dark matter. After the first matter condensed and radiation travelled away, an inhomogeneous web of dark matter, matter that feels only gravity, began to collapse into halos and filaments. These invisible scaffolds attracted hydrogen and helium, drawing the first stars and galaxies into the embrace of invisible hands. The structure we see today, vast filaments and clusters separated by voids, is written by dark matter's script. Galaxies form inside the gravitational wells created by these halos. Without dark matter, the universe would be formless, empty, silent except for the faintest of redshifted cries. Dark matter makes up the bones of cosmic structure. Light tells the story of expansion. Redshift is the siren song. They are the universe's proof that space is not a stage. Space is an actor, alive, expanding, insisting each moment is new. Distance is not what you think it is. It is not a line drawn in stone. It is a relationship, and that relationship is changing. When cosmologists speak of the universe expanding, they do not mean galaxies are flying through space like bullets through air. They mean the metric of space-time itself is growing. The metric is the mathematical description of distance and time, the ruler that tells you how far apart 2 points are and how much time elapses between events. In an expanding universe, that ruler is stretching. A galaxy 1 billion light-years away today will be farther tomorrow, not because it moved, but because the space between here and there multiplied. This is metric expansion, and it is the most fundamental feature of modern cosmology. It is why distant galaxies appear to recede. It is why the cosmic microwave background has cooled from thousands of degrees to less than 3 degrees above absolute zero. It is why we can trace the history of the universe back to a moment 13.8 billion years ago, when all of space was compressed into a volume smaller than an atom. The mathematics of metric expansion come from Einstein's general relativity. The Friedmann equations, derived by Alexander Friedmann in 1922, describe how the scale factor of the universe changes over time. The scale factor is a number that tells you how much space has stretched since the Big Bang. If the scale factor was 1 yesterday and 2 today, then every distance in the universe has doubled. Galaxies that were 1 billion light-years apart are now 2 billion light-years apart. The rate at which the scale factor changes is the Hubble constant, the number that describes how fast the universe is expanding. Today, the Hubble constant is approximately 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space is stretching by 70 kilometers every second. A galaxy 326 million light-years away appears to recede at 7,000 kilometers per second. A galaxy 3.26 billion light-years away appears to recede at 70,000 kilometers per second. The farther the galaxy, the faster it recedes. But this does not mean the galaxies are moving through space. They are carried by space. The distinction is subtle but essential. Motion through space is limited by the speed of light. Nothing with mass can travel faster than 300,000 kilometers per second. But the expansion of space has no such limit. Distant galaxies can recede faster than light because they are not moving. The distance between them and us is growing. This is how the observable universe can be 46.5 billion light-years in radius, even though the universe is only 13.8 billion years old. Light from the most distant galaxies has been travelling for 13.8 billion years, but those galaxies are no longer where they were when the light was emitted. Space has expanded while the light was in transit. The galaxy that emitted the light is now 46.5 billion light-years away, carried by the relentless stretching of space-time. The age of the universe is tied directly to the expansion rate. If you know the Hubble constant, you can calculate how long ago the universe was compressed into a point. This calculation depends on the composition of the universe. A universe dominated by matter expands more slowly over time, because gravity slows the expansion. A universe dominated by dark energy expands faster over time, because dark energy pushes space apart. The most precise measurements of the age come from the cosmic microwave background. Satellites like WMAP and Planck measured the temperature fluctuations in this ancient light and used them to calculate the density of matter, the density of dark energy, and the curvature of space. By plugging these numbers into the Friedmann equations, cosmologists determined that the universe is 13.787 billion years old, with an uncertainty of only 20 million years. This is 99.8% accuracy. But there is a second method. Astronomers can estimate the age by observing the oldest stars. Globular clusters, dense collections of ancient stars, contain objects that formed within the first billion years after the Big Bang. By measuring the brightness, temperature, and chemical composition of these stars, astronomers can calculate their ages. The oldest stars are about 13 billion years old, slightly younger than the universe itself. This consistency between the two methods is a powerful confirmation that the expansion model is correct. The metric expansion is not an abstraction. It is measured, observed, and confirmed by multiple independent lines of evidence. It is the reason the universe has a history. It is the reason time has a beginning. It is the reason we can look into the past by looking into the distance. Every photon that reaches us from a distant galaxy carries the signature of expansion, the redshift that proves space itself has grown. The metric is the fabric of reality, and that fabric is stretching. You're expanding, or are you? The universe is stretching, space itself is multiplying, but your body is not growing. Neither is the Earth, neither is the Milky Way. The expansion of the cosmos does not touch the things that are held together by stronger forces. This is the distinction between local and cosmic scales, and it is the reason you're not being pulled apart. Gravity, electromagnetism, and the nuclear forces bind atoms, planets, stars, and galaxies into stable structures. These forces are far stronger than the expansion of space. Within the gravitational well of a galaxy, space is not expanding. The metric is fixed. Distance is constant. Imagine 2 grains of sand on a rubber sheet. If the sheet is stretched slowly, the grains move apart, but if you glue them together, the stretching has no effect. The glue is stronger than the tension in the sheet. Gravity is the glue. It holds galaxies, galaxy clusters, and even superclusters together. Within these structures, the expansion of the universe is irrelevant. The Milky Way and the Andromeda Galaxy are gravitationally bound. They are not receding from each other. In fact, they are moving toward each other at about 110 kilometers per second. In roughly 4.5 billion years, they will collide and merge into a single elliptical galaxy. The expansion of space between them is insignificant compared to the gravitational attraction pulling them together. This is true for all gravitationally bound systems. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and about 80 smaller galaxies, is not expanding. The Virgo supercluster, a larger structure containing thousands of galaxies, is also held together by gravity. The expansion of space occurs only in the voids between these massive structures, where gravity is weak. On even smaller scales, the forces are even stronger. The electromagnetic force holds atoms together. The strong nuclear force binds protons and neutrons into atomic nuclei. These forces are trillions of times stronger than the expansion of space. The universe could expand forever, and your atoms would remain intact. But the distinction between local and cosmic scales has profound implications for the future of the universe. If dark energy continues to drive the expansion, the voids between galaxy clusters will grow. Clusters that are not yet gravitationally bound will move apart, eventually disappearing beyond the cosmic horizon. Billions of years from now, galaxies outside the local group will be so far away that their light will no longer reach us. The universe will appear smaller, darker, emptier. Recent observations, however, suggest something unexpected. New research published in November 2025 indicates that the universe's expansion may actually be slowing down rather than speeding up. Analysis of corrected supernova data, combined with baryonic acoustic oscillations and cosmic microwave background measurements, suggests that dark energy is not constant. It is evolving, weakening over time. If this finding is confirmed, it represents a potential paradigm shift in cosmology. For nearly 3 decades, scientists have believed that the universe is accelerating toward an endless expansion, a slow heat death in which galaxies drift apart, stars burn out, and the cosmos fades into darkness. But if dark energy is weakening, the expansion could eventually stop. Gravity would take over. The universe would begin to contract. This scenario is known as the Big Crunch. Instead of expanding forever, the universe would collapse back on itself, reversing the Big Bang. Galaxies would rush together. Space would shrink. Eventually, all matter and energy would be compressed into a single point, a singularity. Some models suggest this could happen in as little as 10 to 20 billion years from now, meaning the universe may be approaching the midpoint of its existence. Other models suggest a different fate. If dark energy continues to strengthen, the expansion could accelerate so violently that even gravitationally bound structures are torn apart. This is the Big Rip. First, galaxy clusters would dissolve, then galaxies, then solar systems, then planets. Eventually, even atoms would be ripped apart as space expanded faster than the forces holding them together. Current estimates suggest this could occur in 22 billion years, though the timeline depends on the nature of dark energy. The future of the universe hinges on the behavior of dark energy. If it remains constant, the universe will expand forever, cooling into a heat death. If it weakens, the universe will contract into a big crunch. If it strengthens, the universe will be torn apart in a big rip. Each scenario leads to a different end, but all of them depend on understanding the distinction between local and cosmic scales. The forces that bind matter together are strong, but they are not infinite. Whether they can withstand the relentless stretching of space-time depends on what dark energy truly is. The universe should not look the same in all directions, but it does. When astronomers map the cosmic microwave background, the faint radiation left over from the Big Bang, they find something astonishing. The temperature is uniform to within 1 part in 100,000. Point your telescope at one edge of the sky, then turn it to the opposite side. The radiation has the same temperature. Regions of space separated by billions of light years, so distant that light could never have travelled between them, are in perfect thermal equilibrium. This is the horizon problem, and it should not be possible. In cosmology, the horizon defines the boundary of what can be observed or influenced. The particle horizon is the distance light could have travelled since the Big Bang. It marks the edge of the observable universe, a sphere roughly 46.5 billion light-years in radius centred on Earth. Anything beyond this boundary is invisible, not because the light is too faint, but because it has not had enough time to reach us. The particle horizon grows as the universe ages. At the moment of the Big Bang, it was 0. After 1 second, light could have travelled 1 light second, about 300,000 kilometres. After 1 year, the horizon was 1 light year across. Today, 13.8 billion years later, the particle horizon spans 46.5 billion light years, larger than the age of the universe would suggest because space itself has been expanding. But there is a second horizon, the event horizon. This is the boundary beyond which events can never affect an observer, even in the infinite future. In an accelerating universe dominated by dark energy, the event horizon is fixed at about 16 billion light-years. Galaxies beyond this boundary are receding so fast that no signal they emit today will ever reach us. They are lost to observation forever. The horizon problem arises when you trace the cosmic microwave background back to its origin. This light was emitted 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. At that time, the particle horizon was much smaller than it is today. Regions of space that appear separated by vast distances now were even farther apart then, accounting for the expansion of space. When cosmologists calculate how large the particle horizon was at that early time, they find that regions on opposite sides of the sky were separated by more than 80 times the distance light could have travelled. These regions were never in causal contact. No signal could have passed between them. They should have had different temperatures, different densities, different histories, and yet they are identical. This uniformity demands an explanation. How did regions that could never communicate come to the same temperature? It is as if you placed 2 thermometers in separate rooms, sealed the doors, and returned hours later to find both reading exactly the same. Without contact, equilibrium should be impossible. The solution is cosmic inflation. In the first fraction of a second after the Big Bang, before the hot dense phase that produced the cosmic microwave background, the universe underwent a period of exponential expansion. Space doubled in size more than 60 times in less than 10^32 seconds. This rapid inflation stretched the universe by a factor of at least 0.26126, possibly much more. Before inflation, the entire observable universe was smaller than an atom. All the regions we see today were close enough to reach thermal equilibrium. They had time to exchange energy, to settle into the same temperature. Then inflation exploded them apart, carrying regions that were once in contact to opposite sides of the cosmos. By the time inflation ended and the hot Big Bang began, these regions were separated by vast distances, far beyond each other's horizons. But they retained the memory of their shared past, their identical temperatures frozen into the fabric of space. This is why the cosmic microwave background looks the same in all directions. The uniformity is not a coincidence. It is evidence that the universe was once much smaller, that all the regions we observe were once in contact, and that inflation stretched them to cosmic scales. The horizon problem is solved not by breaking causality, but by revealing that the boundaries we see today are illusions, artifacts of a universe that grew faster than light. The horizon also defines the limits of what we can ever know. Galaxies beyond the event horizon are lost to us. Their light will never arrive. As dark energy drives the expansion faster, the event horizon shrinks in comoving coordinates. More galaxies disappear beyond the boundary every moment. Billions of years from now, observers in the Milky Way will see a much smaller universe, emptier and darker, with only the local group visible. The cosmic horizon is not just a boundary in space, it is a boundary in time, a limit on information, a frontier beyond which the universe becomes unknowable. In less time than it takes light to cross an atom, the universe doubled in size more than 60 times. This is cosmic inflation, a period of expansion so violent that it took a region smaller than a proton and stretched it to the size of a galaxy in a fraction of a heartbeat. The entire observable universe, everything we can see or ever will see, originated from a patch of space so small it would have been invisible even if atoms existed yet. They did not. At that moment, the universe was too hot for matter. There was only energy, a roiling quantum foam where particles flickered in and out of existence, and space itself was about to explode. Inflation occurred in the first trillionth of a trillionth of a trillionth of a second after the Big Bang, driven by a field called the inflaton. This field had a peculiar property: negative pressure. In ordinary physics, pressure pushes things apart, but negative pressure acts like tension, like a stretched rubber band. It pulls on the fabric of space, causing it to expand at an accelerating rate. Every 100 millionth of a trillionth of a trillionth of a trillionth of a second, the universe doubled in size. After just 60 doublings, the scale factor grew by more than 1 billion times. A region the size of a proton became larger than the observable universe today. This wild growth solved 3 fundamental problems with the Big Bang model. The first was the flatness problem. The universe appears geometrically flat, meaning parallel lines remain parallel across cosmic distances. But for this to be true today, the initial density of the universe had to be tuned to extraordinary precision, accurate to 1 part in a number with 60 zeros after it. Any deviation would have caused space to curve into a sphere or a saddle shape. Inflation solved this by stretching space so rapidly that any initial curvature was flattened out, like pulling a wrinkled bedsheet taut. The second was the horizon problem. Regions of the cosmic microwave background separated by vast distances have the same temperature to within 1 part in 100,000, yet they were never in causal contact. Inflation solved this by proposing that all the regions we see today were once close enough to reach thermal equilibrium before being blown apart. The uniformity we observe is not a coincidence, it is memory, frozen into the fabric of space. The third was the magnetic monopole problem. Grand unified theories predict that the early universe should have produced massive magnetic monopoles, particles with only a north or south pole. These monopoles should dominate the universe, yet none have ever been found. Inflation solved this by diluting them. If monopoles formed before inflation, the wild expansion spread them so thin that the chances of encountering one are effectively zero. But inflation's most profound consequence is not what it solved, it is what it created. The cosmic microwave background is not perfectly smooth. It has tiny temperature fluctuations, variations of only a few parts in 100,000. Some regions are slightly warmer, others slightly cooler. These fluctuations are the seeds of everything that exists today: galaxies, stars, planets, life. Without them, the universe would be a featureless void, an endless fog of hydrogen and helium with no structure, no light, no destiny. These temperature fluctuations originated as quantum fluctuations during inflation. At the smallest scales, the quantum uncertainty principle ensures that energy and density are never perfectly uniform. Tiny ripples in the inflaton field flickered in and out of existence, microscopic variations governed by the same laws that prevent electrons from sitting still in atoms. Inflation stretched these quantum fluctuations to cosmic scales. A ripple the size of a proton became the size of a galaxy. A fluctuation that lasted less than a billionth of a billionth of a billionth of a billionth of a second was frozen into the fabric of space, preserved for billions of years. When inflation ended, these variations became density perturbations in the primordial plasma. Regions that were slightly denser collapsed under gravity, forming the first structures. Regions that were slightly less dense became voids. The pattern of these fluctuations is written in the cosmic microwave background. Satellites like COBE, Doppler Map, and Planck measured the temperature variations across the entire sky, creating maps of the universe as it appeared 380,000 years after the Big Bang. The data reveals a characteristic pattern, a statistical signature that matches the predictions of quantum fluctuations stretched by inflation. The power spectrum of the fluctuations, a graph that shows how much variation exists at different angular scales, has peaks and valleys exactly where inflation predicts. This is not an accident. It is evidence that the universe we inhabit was born from quantum noise, amplified by the wild expansion of space in the first moment of time. The galaxies are echoes, the stars are after images. The patterns in the cosmic microwave background are the fingerprints of a universe that grew faster than light, seeded by fluctuations too small to see, stretched to scales too vast to comprehend. Something is tearing the universe apart, and we do not know what it is. In 1998, two teams of astronomers studying distant supernovae made a discovery that shattered every expectation. They were measuring the expansion rate of the universe across cosmic time, trying to determine whether gravity was slowing the expansion down. The prediction was simple: the universe should be decelerating. Gravity pulls everything together. Over billions of years, that pull should gradually slow the cosmic expansion, like a ball thrown upward that slows as it climbs. But the data showed the opposite. The universe was not slowing down. It was speeding up. Distant supernovae, used as standard candles to measure cosmic distances, appeared dimmer than expected. This meant they were farther away than they should have been if the expansion rate was constant or slowing. The only way to explain the observations was if space itself was expanding faster now than it did billions of years ago. Something was pushing the universe apart with increasing force. This invisible force is called dark energy, and it dominates the cosmos. Roughly 68% of the universe is composed of dark energy. It does not emit light. It does not interact with matter. It does not clump into galaxies or stars. It simply fills all of space, exerting a repulsive pressure that drives the expansion faster and faster. Dark energy is not like ordinary energy. It does not dilute as space expands. When the universe doubles in size, the density of matter drops by a factor of 8. The density of radiation drops by a factor of 16. But the density of dark energy remains constant. As space grows, more dark energy appears, maintaining the same energy per unit volume. This means the total amount of dark energy in the universe is increasing every moment. The simplest explanation for dark energy is the cosmological constant, the term Einstein added to his equations in 1917 and later called his greatest blunder. The cosmological constant represents the energy of empty space itself, a baseline level of energy woven into the fabric of the vacuum. Quantum field theory predicts that even empty space should have energy, arising from virtual particles that flicker in and out of existence. But there is a catastrophic problem. When physicists calculate what the vacuum energy should be based on quantum mechanics, they get a number that is 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics, off by more than 100 orders of magnitude. Something is cancelling out almost all of the vacuum energy, leaving behind only a tiny residual that drives the accelerated expansion. No one knows what that something is. This is the cosmological constant problem, and it remains one of the deepest mysteries in physics. Why is the vacuum energy so small? Why is it not zero? And why does its value happen to be similar to the density of matter in the universe today? These questions have no satisfactory answers. Some cosmologists have proposed alternatives to the cosmological constant. Instead of a fixed energy density, dark energy could be a dynamic field that changes over time, similar to the inflaton field that drove cosmic inflation. This hypothetical field is called quintessence. Unlike the cosmological constant, quintessence can vary in strength, potentially growing stronger or weaker as the universe ages. Recent observations suggest that dark energy may indeed be evolving. Analysis of supernova data combined with measurements of the cosmic microwave background and baryon acoustic oscillations indicates that the strength of dark energy might be weakening over time. If confirmed, this would rule out the cosmological constant and suggest that dark energy is a dynamic force, not a static property of space. The implications are profound. If dark energy is constant, the universe will expand forever, accelerating into an endless heat death. Galaxies will drift apart, stars will burn out, the cosmos will fade into darkness. But if dark energy is weakening, the expansion could eventually stop. Gravity would take over, and the universe would collapse back on itself in a big crunch. If dark energy is strengthening, the expansion could accelerate so violently that even atoms are torn apart in a big rip. Dark energy is the invisible hand reshaping the universe. It is the reason distant galaxies recede faster every year. It is the reason the cosmos will never collapse. It is the reason the future is written in acceleration, not stillness. And we do not understand it at all. Einstein added it to stop the universe from moving. Decades later, it became the force tearing the cosmos apart. In 1917, Albert Einstein faced a problem. His equations of general relativity described gravity as the curvature of space-time, a revolutionary idea that explained everything from the orbit of Mercury to the bending of light around the sun. But when he applied those equations to the universe as a whole, they predicted something he could not accept. The universe could not stand still. It had to be either expanding or contracting. At the time, every observation suggested the cosmos was eternal and unchanging. The idea of a dynamic universe struck Einstein as absurd, so he modified his equations, adding a new term represented by the Greek letter lambda. This was the cosmological constant, a repulsive force that could balance gravity and hold the universe in place. It was mathematical scaffolding, a fudge factor designed to preserve the static cosmos he believed in. But the universe does not care what we believe. In 1929, Edwin Hubble discovered that galaxies are receding, proving the cosmos is expanding. Einstein abandoned the cosmological constant and called it his greatest blunder. For decades, physicists assumed lambda was zero, a relic of a discarded idea. Then, in 1998, the universe revealed its secret. Two teams of astronomers studying distant supernovae found that the expansion of space is not slowing down. It is accelerating. Gravity should be pulling the universe back together, slowing the expansion over billions of years. Instead, something is pushing galaxies apart faster and faster. Einstein's cosmological constant had returned, not as a tool to hold the universe still, but as the dominant force shaping its future. The simplest explanation for the accelerated expansion is that empty space has energy. Quantum field theory predicts that even a perfect vacuum is not truly empty. Virtual particles flicker in and out of existence, borrowing energy from the vacuum for infinitesimal moments before vanishing. This quantum foam creates a baseline energy density, a pressure woven into the fabric of space itself. This vacuum energy acts like the cosmological constant. It does not clump into galaxies or stars. It does not dilute as space expands. It simply fills all of space with a constant energy density, exerting a repulsive pressure that drives the expansion faster. As the universe grows, more vacuum energy appears, maintaining the same energy per unit volume. The total amount of dark energy in the cosmos increases every moment. But there is a catastrophic problem. When physicists calculate what the vacuum energy should be based on quantum mechanics, the answer is absurdly wrong. The prediction is larger than what we observe by a factor of 10 to the power of 120. This is the worst mismatch between theory and observation in the history of science, off by more than 100 orders of magnitude. Something is cancelling out almost all of the vacuum energy, leaving behind only a tiny residual that drives cosmic acceleration. No one knows what that something is. This is the cosmological constant problem, and it remains one of the deepest mysteries in physics. Why is the vacuum energy so small? Why is it not zero? And why does its value happen to be similar to the density of matter in the universe today? Roughly 68% of the total energy budget. These questions have no satisfactory answers. The cosmological constant also determines the fate of the universe. If lambda remains constant, the expansion will continue to accelerate forever. Galaxies not gravitationally bound to the Milky Way will drift beyond the cosmic horizon, disappearing from view. Billions of years from now, the observable universe will shrink to just the local group. Stars will burn out, black holes will evaporate, the cosmos will fade into a cold, dark, empty void. This is the heat death, the slow dimming of the universe into eternal stillness. But recent observations suggest the cosmological constant may not be constant at all. Analysis published in November 2025 indicates that dark energy might be weakening over time. If this is true, the universe's expansion could eventually stop. Gravity would take over, pulling galaxies back together. The cosmos would collapse in a big crunch, a reverse Big Bang that compresses all matter and energy into a single point. Alternatively, if dark energy strengthens, the acceleration could become so violent that even atoms are torn apart. This is the Big Rip, a scenario in which the fabric of space expands faster than the forces holding matter together. First, galaxy clusters dissolve, then galaxies, then solar systems, then planets. Eventually, even atomic nuclei are ripped apart. Current estimates suggest this could occur in 22 billion years if dark energy follows this trajectory. The cosmological constant is not just a number in an equation. It is the invisible hand reshaping the universe. It is the reason distant galaxies recede faster every year. It is the reason the cosmos will never collapse under its own gravity. It is the reason the future is written in acceleration, not stillness. And after more than a century, we still do not understand it at all. In 1998, the universe broke physics. Two teams of astronomers were hunting for distant supernovae, stellar explosions so bright they can outshine entire galaxies. They were using these supernovae as cosmic yardsticks, measuring how fast the universe was expanding at different points in its history. The expectation was simple. Gravity pulls everything together, so the expansion should be slowing down. The universe should be decelerating like a ball thrown upward that gradually loses speed as gravity pulls it back. But the data told a different story. The distant supernovae appeared dimmer than expected, which meant they were farther away than they should have been. The only way to explain this was if the universe had been expanding faster and faster over time. Space itself was accelerating. The discovery stunned the scientific community. Adam Rees, Saul Perlmutter, and Brian Schmidt led the two independent teams, and their findings were so revolutionary that they earned the Nobel Prize in Physics in 2011. For the first time in history, humanity had direct evidence that something was pushing the universe apart with increasing force, that something is dark energy. 9 billion years after the Big Bang, the universe reached a turning point. For the first half of cosmic history, matter dominated. Gravity slowed the expansion, pulling galaxies together, but as space grew, the density of matter dropped. Dark energy, which does not dilute as the universe expands, began to take over. The repulsive pressure of dark energy overpowered gravity, and the expansion started to accelerate. This acceleration has profound consequences. Galaxies that are not gravitationally bound to the Milky Way are moving away faster every year. The more distant they are, the faster they recede. Eventually, they will cross the cosmic horizon, the boundary beyond which no light can ever reach us. Billions of years from now, observers in the Milky Way will see a much smaller universe, with only the local group of galaxies visible. Everything else will have vanished beyond the edge of the observable cosmos. But recent observations suggest the story may be more complicated. In November 2025, a new study published by physicist Yongchan Li and his team cast doubt on the idea that the universe is still accelerating. Using corrected supernova data combined with measurements of baryon acoustic oscillations and the cosmic microwave background, They found evidence that the expansion may already be slowing down. If this finding is confirmed, it would mean that dark energy is not constant. It is evolving, weakening over time. This would represent a paradigm shift in cosmology. Instead of a universe doomed to accelerate forever into a cold, dark heat death, we might be living in a cosmos that will eventually stop expanding and begin to contract. The evidence comes from multiple independent sources. The dark energy spectroscopic instrument known as DESI released data in March 2025 showing hints that dark energy may not remain constant over cosmic time. Using 15 million galaxies and quasars, DESI created the largest three-dimensional map of the universe ever made, tracing the evolution of cosmic structures over the past 11 billion years. The data suggests that the density of dark energy has decreased by about 10% over the last few billion years. This is not much, far less than the decrease in the density of matter and radiation, but it is significant. If dark energy is weakening, the acceleration of the universe is also weakening. The expansion will continue for billions of years, but it may eventually stop. What happens next depends on how dark energy evolves. If dark energy continues to weaken, gravity will eventually dominate. The universe will collapse back on itself in a big crunch, a reverse Big Bang that compresses all matter and energy into a singularity. If dark energy remains constant, the universe will expand forever, accelerating into an endless heat death. If dark energy strengthens, the expansion will accelerate so violently that even atoms are torn apart in a big rip. The fate of the universe hangs on the behavior of dark energy, and for the first time in decades, the evidence suggests that the cosmological constant may not be constant after all. The universe is still expanding, but whether it will do so forever is no longer certain. The universe is mostly something we do not understand. Dark energy makes up roughly 68% of the total energy budget of the cosmos. It is not matter. It is not radiation. It is not any form of energy we have ever encountered in a laboratory. It does not emit light, does not interact with particles, and cannot be directly detected. Its existence is inferred entirely from its gravitational effects on the expansion of space, and despite decades of observation and theory, we have no idea what it is. The remaining 32% of the universe is split between dark matter and ordinary matter. Dark matter, invisible and mysterious in its own right, makes up about 27%. Ordinary matter, the stuff of stars, planets, and life, accounts for less than 5%. Everything humanity has ever observed, every galaxy mapped, every atom studied, represents a tiny fraction of the cosmos. The vast majority of reality is hidden from view. Dark energy reveals itself through cosmic acceleration. In the late 1990s, two teams of astronomers studying distant supernovae discovered that the universe is expanding faster now than it was billions of years ago. This was the opposite of what physics predicted. Gravity should slow the expansion. Instead, something was pushing galaxies apart with increasing force. That something is dark energy. The simplest explanation is that dark energy is the cosmological constant, a fixed energy density woven into the fabric of space itself. In this model, empty space has energy, a baseline level of quantum activity that exerts a repulsive pressure. As the universe expands, more space is created and more dark energy appears, maintaining a constant energy per unit volume. The total amount of dark energy grows over time, driving the acceleration. But recent observations suggest dark energy may not be constant after all. In March 2025, the Dark Energy Spectroscopic Instrument, known as DESI, released new data based on 3 years of observations. The telescope, perched atop Kitt Peak in Arizona, has observed nearly 15 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever made. The data spans the last 11 billion years of cosmic history, tracing how the universe has expanded over time. When DESI's observations are combined with measurements of the cosmic microwave background, supernova distances, and weak gravitational lensing, the standard model of cosmology struggles to explain all the data. The lambda CDM model, which assumes dark energy is a cosmological constant, does not fit the observations as well as models in which dark energy evolves over time. The evidence for evolving dark energy ranges from 2.8 to 4.2 sigma, depending on which datasets are combined. A 3 sigma result has about a 0.3% chance of being a statistical fluke. A 5 sigma result, the threshold physicists require to confirm a discovery, has less than a 1 in a million chance of being random. Desi's findings are not yet at that level, but they are strong enough to command attention. The data suggests that the density of dark energy has decreased by about 10% over the past few billion years. This is a subtle change, far less than the decrease in the density of matter and radiation as the universe expands. But it is significant. If dark energy is weakening, the acceleration of the universe is also weakening. The cosmos will continue to expand for billions of years, but the rate of expansion may not increase forever. The Dark Energy Survey, an independent project based in the Chilean Andes, has reached similar conclusions. Using 5 years of high-resolution photographs covering 12% of the sky, the survey catalogued millions of galaxies and supernovae. When combined with cosmic microwave background data, the results show a tension with the lambda CDM model at 3.2 sigma. The tension disappears when dark energy is allowed to evolve. The evidence is mounting, but cosmologists remain cautious. Past anomalies in physics have melted away with additional data, and researchers are careful not to overstate their findings. DESI has extensive procedures to avoid systematic errors, including blinding strategies that prevent scientists from biasing their analysis. The collaboration has performed numerous additional tests compared to their first-year results, and the preference for evolving dark energy has strengthened, not weakened. If dark energy is truly evolving, it would rewrite the future of the universe. A constant cosmological constant predicts an endless acceleration, a cold heat death in which galaxies disappear beyond the horizon and stars fade into darkness. But evolving dark energy opens other possibilities. The expansion could stop, the universe could collapse, or dark energy could change in ways we cannot yet predict. The cosmos is 68% mystery, and that mystery may be changing. Empty space is not empty, it seethes with energy. Quantum field theory, the most successful framework in physics, predicts that even a perfect vacuum should contain energy. Particles and antiparticles flicker in and out of existence at scales so small and times so brief they cannot be directly observed. These are virtual particles, born from the uncertainty principle, borrowing energy from the vacuum for fractions of a second before annihilating back into nothingness. This quantum foam is not a theoretical abstraction. It has been measured. The Casimir effect, where two metal plates placed close together in a vacuum experience a measurable force, is direct evidence that empty space has structure. This vacuum energy should have a gravitational effect. Einstein's equations of general relativity treat all forms of energy as sources of gravity, and vacuum energy is no exception. But unlike ordinary matter, which pulls things together, vacuum energy has negative pressure. It pushes. This repulsive force acts on the fabric of space itself, causing it to expand faster and faster. The cosmological constant, the simplest explanation for dark energy, is the energy of the vacuum. It represents a baseline level of energy density that fills all of space uniformly. As the universe expands, the density of matter drops. The density of radiation drops even faster. But the density of vacuum energy remains constant. Every cubic meter of space has the same amount of dark energy, whether that cubic meter existed at the Big Bang or was created by the expansion yesterday. This means the total amount of dark energy in the universe is increasing every moment. But there is a catastrophic problem. When physicists calculate what the vacuum energy should be based on quantum mechanics, the prediction is absurdly wrong. The calculation involves summing up the energy contributions from all possible virtual particles at all possible wavelengths. The result is infinite. To make sense of this, physicists impose a cutoff at the Planck scale, the smallest meaningful length in physics, about 10 to the power of negative 35 meters. Even with this cutoff, the predicted vacuum energy is 10 to the power of 120 times larger than what we observe. This is the worst prediction in the history of science. Theory and observation disagree by more than 100 orders of magnitude. Something is cancelling out almost all of the vacuum energy, leaving behind only a tiny residual that drives the accelerated expansion. No one knows what that something is. No symmetry, no mechanism, no principle in physics explains why the vacuum energy should be so small. Some physicists have proposed that the observed value of the cosmological constant is a result of the anthropic principle. In a multiverse with countless bubble universes, each with different values of the fundamental constants, only those universes with very small cosmological constants can form galaxies, stars, and planets. If the cosmological constant were much larger, the universe would have expanded so rapidly that matter could never have clumped together. If it were negative, the universe would have collapsed long before stars could form. We observe a small cosmological constant because we exist in a universe where life is possible. But this explanation is deeply unsatisfying to many physicists. It abandons the search for a fundamental reason and replaces it with probabilistic selection. It suggests the vacuum energy is not determined by the laws of physics, but by the requirement that observers must exist to measure it. Alternatives to the cosmological constant have been proposed. Instead of a fixed energy density, dark energy could be a dynamic field that changes over time. This field, called quintessence, would have an energy density that evolves as the universe expands. Unlike the cosmological constant, quintessence can vary in strength, potentially growing weaker or stronger as cosmic history unfolds. Recent observations from the Dark Energy Spectroscopic Instrument and the Dark Energy Survey suggest that dark energy may indeed be evolving. The data hints that the density of dark energy has decreased by about 10% over the past few billion years. If confirmed, this would rule out the cosmological constant and suggest that dark energy is a dynamic force, not a static property of the vacuum. But the vacuum's power remains the leading explanation. For all its problems, the cosmological constant fits most of the data. It is simple, requiring only a single number to describe it. It is consistent with general relativity. And it matches the observed acceleration of the universe to high precision. The vacuum may be the engine driving the cosmos apart, filling space with invisible energy, reshaping the future 1 cubic meter at a time. The universe should not exist, or at least it should not look like this. When physicists calculate what the energy of empty space should be, they arrive at a number so catastrophically wrong that it defies comprehension. The prediction from quantum field theory is larger than the observed value of dark energy by a factor of 10 to the power of 120. This is not a small error. It is not a rounding mistake. It is the worst mismatch between theory and observation in the history of science. This is the lambda problem, also known as the cosmological constant problem, and it has haunted physics for decades. The Greek letter lambda represents the cosmological constant in Einstein's equations, the term that describes the energy density of empty space. Observations tell us that this value is tiny but not zero. It is roughly equivalent to 1 joule of energy per cubic kilometre of space. This is an absurdly small number, but it is not nothing, and that is the problem. Quantum mechanics predicts that even a perfect vacuum should be filled with energy. Virtual particles, fleeting ghosts of matter and antimatter, pop in and out of existence at the smallest scales. These quantum fluctuations contribute to the energy density of space. When physicists sum up the contributions from all possible particles at all possible wavelengths, the result is infinite. To make sense of this, they impose a cutoff at the Planck length, the smallest meaningful distance in physics, about 10 to the power of negative 35 meters. Even with this cutoff, the predicted vacuum energy is enormous. The observed value of the cosmological constant is roughly 1 followed by 120 zeros smaller than the prediction. If you wrote out the ratio, the number would stretch across a page. Something is cancelling out almost all of the vacuum energy, leaving behind only the tiniest residual. But no one knows what that something is. This is not just an academic puzzle. The value of the cosmological constant determines the fate of the universe. If it were much larger, space would have expanded so rapidly that galaxies could never have formed. Stars would never have ignited. Planets would never have coalesced. Life would be impossible. If it were negative, gravity would have overpowered the expansion, and the universe would have collapsed back on itself long before the first atoms formed. The fact that the cosmological constant has precisely the value needed for structure to form has led some physicists to invoke the anthropic principle. In a multiverse containing countless bubble universes, each with different values of the fundamental constants, only those universes with very small cosmological constants can support life. We observe this particular value not because it is predicted by the laws of physics, but because we could not exist in a universe where it was much different. But this explanation is deeply unsatisfying. It replaces the search for a fundamental mechanism with probabilistic selection. It suggests that the cosmological constant is not determined by any principle, but by the requirement that observers must exist to measure it. Many physicists regard this as giving up, a retreat from the goal of understanding why the universe has the properties it does. Others have proposed that the vacuum energy is exactly zero, and that dark energy arises from a different source entirely. Instead of a fixed constant, dark energy could be a dynamic field that changes over time, similar to the inflaton field that drove cosmic inflation. This field, called quintessence, would have an energy density that evolves as the universe expands. Unlike the cosmological constant, quintessence can vary in strength, weakening or strengthening as the cosmos ages. Recent observations support this possibility. Data from the Dark Energy Spectroscopic Instrument and the Dark Energy Survey suggest that the density of dark energy has decreased by about 10% over the past few billion years. If this finding is confirmed, it would mean the cosmological constant is not constant at all, and dark energy is something more complex than vacuum energy. But even if dark energy is dynamical, the lambda problem does not go away. The energy density of quintessence is still incredibly small compared to what quantum field theory predicts. Whatever mechanism is suppressing the vacuum energy, it must still be operating, cancelling out the enormous contributions from quantum fluctuations and leaving behind only a tiny residual. The lambda problem remains one of the deepest mysteries in physics. It sits at the intersection of quantum mechanics, general relativity and cosmology, and no existing theory can explain it. The universe exists in a state of extraordinary fine-tuning, balanced on the edge of a knife, and we do not know why. The universe has no centre and no edge, but it is not infinite. This is the paradox of a finite but unbounded cosmos, a geometry so counterintuitive that the human mind struggles to picture it. Imagine the surface of a sphere. An ant crawling on that surface could travel in any direction forever, never reaching a boundary, never finding an edge. Yet the surface is not infinite. It has a finite area. There is no special point on the sphere, no centre, no corner. Every location looks the same as every other. This is how the universe may be shaped, not as a three-dimensional sphere embedded in some higher space, but as a curved three-dimensional fabric that folds back on itself. Space could be finite in volume but unbounded in extent, with no walls to mark its limits, no border beyond which nothing exists. You could travel in a straight line for trillions of years and never reach an edge, yet you would eventually return to where you started. General relativity allows for three possible geometries of the universe, determined by the density of matter and energy. If the density is greater than a critical value, space curves into a closed shape, like the surface of a sphere. This is a finite universe. If the density is less than the critical value, space curves into an open shape, like the surface of a saddle. This is an infinite universe. If the density equals the critical value exactly, space is flat, extending infinitely in all directions. Observations suggest the universe is flat, or very close to it. The cosmic microwave background, mapped by satellites like WMAP and Planck, shows temperature fluctuations that match the predictions of a flat geometry to extraordinary precision. The curvature of space, if it exists at all, is so small that it could not be detected even with the most sensitive instruments. But flatness does not necessarily mean infinite. A flat universe could be finite if it has an unusual topology, a shape that wraps around on itself. Imagine a video game where moving off the right edge of the screen brings you back on the left. The screen is flat, but the space is finite and repeating. The universe could work the same way, with space folding back on itself in ways that are difficult to visualize but mathematically consistent. Astronomers have searched for evidence of this topology by looking for repeating patterns in the cosmic microwave background. If the universe wraps around on itself, light from distant galaxies could take multiple paths to reach us, creating identical images in different parts of the sky. So far, no such patterns have been found. If the universe is finite, it is larger than the observable universe, extending beyond the cosmic horizon. The question of whether the universe is finite or infinite has profound implications. An infinite universe contains an infinite amount of matter and energy. Every possible configuration of particles, every possible history, would exist somewhere. There would be infinite copies of you, living infinite variations of your life. An infinite universe is a multiverse by default, containing all possibilities. A finite universe, by contrast, contains a limited amount of matter and energy. It has a finite volume, a finite number of particles, a finite number of states. The cosmos is unique, bounded not by walls but by its own geometry. There is only one you, one Earth, one history. But finite or infinite, the universe is unbounded. There is no edge, no boundary, no place where space ends and something else begins. The cosmos does not sit inside anything. It does not expand into anything. It is the totality of existence, the only arena where events can unfold. Whether it stretches forever or curves back on itself, the universe refuses to give us the comfort of walls. 46.5 billion light years. That is the radius of everything we can ever see. This is the particle horizon, the boundary of the observable universe. It is a sphere centered on Earth, stretching in all directions to the farthest distance from which light could have traveled since the Big Bang. Beyond this boundary lies the unobservable cosmos, regions of space that are forever hidden from view. Not because the light is too faint, but because it has not had enough time to reach us. The observable universe is not the entire universe. It is only the portion we can see. The full cosmos may be much larger, possibly infinite, but the observable universe is finite, limited by the speed of light and the age of the cosmos. 13.8 billion years after the Big Bang, light from the most distant galaxies has travelled for the entire history of the universe. That light defines the edge of what we can observe. But the observable universe is larger than 13.8 billion light-years in radius. It is 46.5 billion light-years. This apparent contradiction arises because space itself has been expanding while the light was in transit. A galaxy that emitted light 13.8 billion years ago was much closer to us then than it is now. Over billions of years, the expansion of space carried that galaxy farther away. By the time its light reaches us, the galaxy is now 46.5 billion light-years distant. The particle horizon grows as the universe ages. At the exact instant of the Big Bang, the particle horizon was 0. After 1 second, light could have travelled 1 light second, about 300,000 kilometres. After 1 year, the horizon was 1 light-year across. Today, after 13.8 billion years, the particle horizon spans 93 billion light-years from edge to edge. It is a sphere that contains everything we have ever observed and everything we could ever observe, given enough time. But there is a second horizon, the event horizon, and it tells a darker story. The event horizon is the boundary beyond which events can never affect an observer, even in the infinite future. It marks the edge of all possible observations. In an accelerating universe dominated by dark energy, the event horizon is fixed at about 16 billion light-years. Galaxies beyond this boundary are receding so fast that no signal they emit today will ever reach us. They are lost to observation forever. This is not because they are moving through space faster than light, which would violate relativity. It is because space itself is expanding faster than light can cross it. The distance between us and those galaxies is growing so rapidly that even a photon travelling at the speed of light cannot close the gap. The light will travel forever, but it will never arrive. The galaxy remains forever beyond the horizon. As dark energy drives the expansion faster, the event horizon shrinks in moving coordinates. More galaxies cross the boundary every moment. Billions of years from now, observers in the Milky Way will see a much smaller universe. Only the local group of galaxies gravitationally bound to the Milky Way will remain visible. Everything else will have vanished beyond the event horizon, swallowed by the accelerating expansion of space. The particle horizon and the event horizon are not the same boundary. The particle horizon represents the past, the limit of what has already been observed. It grows as the universe ages, encompassing more and more distant regions. The event horizon represents the future, the limit of what will ever be observed. In an accelerating universe, it does not grow. It remains fixed, or even shrinks, as dark energy tears the cosmos apart. Between these two horizons lies the Hubble sphere, the region of space where galaxies recede at the speed of light. Inside the Hubble sphere, galaxies recede slower than light. Outside, they recede faster. The Hubble sphere is not a fixed boundary. It evolves as the expansion rate changes. In a decelerating universe, the Hubble sphere grows. In an accelerating universe, it shrinks. The observable universe is a prison of light and time. We can see only what light has had time to show us, and light travels at a finite speed. The horizon is not a wall. It is a consequence of the finite age of the cosmos and the relentless expansion of space. Beyond the horizon lies the rest of reality, forever hidden, forever unknowable. The universe extends beyond what we can see, but what we can see is all we will ever have. Galaxies are disappearing. Right now, as you read this, entire clusters of stars are crossing a boundary they will never return from. This is not death. It is exile. These galaxies are not being destroyed. They are simply receding so fast that no light they emit today will ever reach us. They are crossing the cosmic event horizon, the invisible line beyond which no signal can ever arrive, and once they cross, they are gone forever. The event horizon is not like the edge of a cliff. It is not a place you can visit. It is a relationship between distance and expansion, a consequence of dark energy driving space apart faster than light can cross it. In an accelerating universe, the event horizon is fixed at about 16 billion light-years. Every galaxy beyond that boundary is already lost, and as the expansion continues, more galaxies will cross the threshold, vanishing from view like ships sailing past the edge of the world. This is different from the particle horizon, the boundary of what we have already observed. The particle horizon grows as the universe ages, encompassing more and more distant regions as light from farther away finally reaches us. The event horizon, by contrast, does not grow. In an accelerating universe dominated by dark energy, it remains fixed or even shrinks. The future is closing in. Today, we can observe galaxies out to the particle horizon, roughly 46.5 billion light-years away. But most of those galaxies are already beyond the event horizon. We see their past, the light they emitted billions of years ago when they were closer to us. But they have been receding ever since. The galaxies that emitted the cosmic microwave background, the oldest light in the universe, are now so far away that they are forever out of reach. We will never see what they look like today. We will never know what became of them. As dark energy drives the expansion faster, the event horizon shrinks in moving coordinates. More galaxies slip beyond the boundary every moment. 1 billion years from now, observers in the Milky Way will see fewer galaxies than we do today. 10 billion years from now, only the local group will remain visible. Everything else will have vanished beyond the horizon, swallowed by the accelerating expansion of space. The universe will appear smaller, darker, emptier. Future astronomers will look up at the night sky and see only the Milky Way, Andromeda, and a handful of dwarf galaxies. They will have no evidence that the universe is expanding because everything beyond the local group will be gone. The cosmic microwave background will have redshifted into invisibility, stretched by the expansion until its photons have wavelengths measured in light-years. The evidence for the Big Bang will have faded into darkness. Future civilizations, if they arise, will have no way to discover what we know today. They will inherit a universe that appears static, eternal, and almost empty. Unless they find records left by earlier civilizations, they will never know that the cosmos was once full of galaxies, that space itself is expanding, or that the universe had a beginning. The accelerating expansion of space is erasing the evidence of its own history. This is the tyranny of the event horizon. It is not just a limit on what we can see, it is a limit on what we can ever know. Information beyond the horizon is not merely inaccessible, it is irrelevant. No signal from those regions can affect us. No force can reach us. No light can arrive. The universe beyond the event horizon might as well not exist. But it does exist. Somewhere beyond the boundary, galaxies are forming, stars are dying, planets are orbiting. Events are unfolding that we will never observe, histories that we will never know. The cosmos is larger than what we can see, vaster than what we can measure, richer than what we can imagine, and most of it is forever hidden, locked beyond a horizon that grows darker with every passing moment. 380,000 years after the Big Bang, the universe became transparent. Before that moment, the cosmos was an opaque fog. The temperature was so high that electrons and protons could not bind together to form atoms. They flew free, colliding endlessly with photons of light. Every photon was scattered almost immediately, unable to travel more than a short distance before smashing into another particle. Light was trapped, pinned in place by the density of matter. The universe glowed like the surface of a star, but nothing could see through it. Then the expansion cooled the plasma below 3000 degrees Kelvin. Electrons and protons combined to form hydrogen atoms. This is called recombination, though it is a misleading term because the particles were combining for the first time. The moment recombination occurred, photons were suddenly free to travel. The fog cleared. Light streamed through the universe for the first time, carrying with it a snapshot of the cosmos as it appeared at that instant. That light has been travelling ever since. It has crossed the expanding universe for 13.8 billion years, stretched by the growth of space from visible light to microwaves. Today, it fills the entire cosmos with a faint glow at a temperature of 2.7 degrees above absolute zero. This is the cosmic microwave background, the oldest light in the universe, a photograph of reality when it was only 380,000 years old. The cosmic microwave background is not a distant object. It is not a shell or a sphere. It is everywhere. Every point in space is filled with this ancient radiation, coming from all directions. The light we observe today was emitted by matter that is now 46 billion light-years away, carried to that distance by the expansion of space. But similar light is arriving from every direction simultaneously, forming a sphere around us called the surface of last scattering. The radiation is remarkably uniform. Point a radio telescope at any patch of sky, and you will measure the same temperature to within 1 part in 25,000. This uniformity is one of the strongest pieces of evidence for the Big Bang. Regions of space separated by vast distances, so far apart that light could never have travelled between them in the time since the Big Bang, have exactly the same temperature. This is the horizon problem, solved by cosmic inflation, which stretched the universe so rapidly that regions once in contact were blown to opposite sides of the sky. But the cosmic microwave background is not perfectly smooth. Embedded in the uniform glow are tiny temperature fluctuations, variations of only a few parts in 100,000. Some regions are slightly warmer, others slightly cooler. These fluctuations are the seeds of everything that exists today. The slightly denser regions collapsed under gravity, forming the first stars, galaxies, and galaxy clusters. The slightly less dense regions became the voids, the great empty spaces between structures. The pattern of these fluctuations holds extraordinary information. The angular scale of the first peak in the power spectrum determines the curvature of the universe. The ratio of the second peak to the first peak reveals the density of ordinary matter. The third peak tells us about dark matter. By analysing the temperature variations across the entire sky, cosmologists have measured the age of the universe, the density of dark energy, and the expansion rate to remarkable precision. Satellites have mapped the cosmic microwave background in ever-increasing detail. The Cosmic Background Explorer, launched in 1989, detected the temperature fluctuations for the first time, confirming predictions of the Big Bang model. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the fluctuations with unprecedented precision. The Planck satellite, launched in 2009, pushed the measurements even further, creating the most detailed map of the early universe ever made. The cosmic microwave background is a gift. It is the only direct observation we have of the universe before stars existed, before galaxies formed, before structure emerged from the primordial plasma. It is a window into a time when the cosmos was simpler, hotter, and more uniform, and it is fading. As the universe expands, the wavelengths of the cosmic microwave background stretch longer. Billions of years from now, the radiation will have redshifted into invisibility. Its photons spread so thin that no detector will ever find them. The evidence for the Big Bang will vanish, leaving future civilizations with no way to discover the history of the cosmos. We're fortunate to live in an era when the light of creation is still visible. The universe looks the same everywhere you point a telescope. This is not an accident. It is a law. Isotropy is the principle that the cosmos appears uniform in all directions. Point a radio telescope at the northern sky and measure the temperature of the cosmic microwave background. Then point it at the southern sky. The temperature is the same to within 1 part in 25,000. Point it east, west, up, down. The result does not change. The universe has no preferred direction. This uniformity is one of the strongest pieces of evidence for the Big Bang. If the universe had been created recently, or if different regions had different histories, we would expect to see variations. But the cosmic microwave background is nearly identical across the entire sky. Regions separated by billions of light years, so far apart that light could never have travelled between them in the time since the Big Bang, have exactly the same temperature. They are in perfect thermal equilibrium. Isotropy extends beyond the cosmic microwave background. The distribution of galaxies is isotropic on large scales. The expansion rate of the universe is the same in all directions. The laws of physics do not depend on which way you are facing. This uniformity suggests that the universe has no centre, no edge, no special location. Every point in space looks roughly like every other point. This is the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. Homogeneous means it looks the same from every location. Isotropic means it looks the same in every direction. Together, these principles imply that there is nothing special about our position in the cosmos. We're not at the centre, we're not at the edge. We are somewhere typical, observing a universe that looks the same from all vantage points. The cosmological principle is not a law of physics. It is an assumption, supported by observation but not required by theory. General relativity allows for universes that are not homogeneous or isotropic. Space could have preferred directions. It could expand faster in some regions than others. But observations show that the real universe, at least on large scales, obeys the cosmological principle. This uniformity is remarkable because it is not obvious. The early universe was a chaotic place, filled with quantum fluctuations and variations in density. Yet somehow, by the time the cosmic microwave background was emitted, the temperature was uniform to within 1 part in 100,000. The horizon problem asks how this is possible. Regions that were never in causal contact should not have the same temperature. Cosmic inflation solves the horizon problem by proposing that the universe underwent a period of rapid expansion in its first fraction of a second. Before inflation, all the regions we observe today were close enough to reach thermal equilibrium. Then, inflation stretched them apart, carrying regions that were once in contact to opposite sides of the observable universe. The isotropy we see is a memory of that shared past, frozen into the fabric of space. But isotropy is not perfect. The cosmic microwave background has tiny temperature fluctuations, variations of a few parts in 100,000. These fluctuations are the seeds of structure, the slight overdensities that collapsed under gravity to form galaxies. The pattern of these fluctuations is also isotropic. There is no preferred direction in which galaxies tend to form. The universe does not favour north over south, east over west. Isotropy is a gift. It simplifies the mathematics of cosmology enormously. If the universe had preferred directions, the equations describing its evolution would be vastly more complicated. The fact that space looks the same in all directions allows cosmologists to model the entire cosmos with just a handful of parameters. The universe is complex, but its large-scale structure is simple. The universe is too uniform, and yet it is not uniform enough. For decades, cosmologists have mapped the cosmic microwave background with ever-increasing precision. The temperature of this ancient radiation is the same in all directions to within 1 part in 25,000. A remarkable testament to the uniformity of the early universe. But embedded in that uniformity are tiny fluctuations, variations of a few parts in 100,000. These fluctuations are the seeds of structure, the slight overdensities that collapsed under gravity to form galaxies. The pattern of these fluctuations is predicted by cosmic inflation. Quantum fluctuations in the early universe were stretched to cosmic scales, frozen into the fabric of space. The statistical properties of these fluctuations should be random, with no preferred direction or location. The universe should be isotropic, looking the same in all directions. But it is not. Several anomalies have been detected in the cosmic microwave background, subtle deviations from the predictions of the standard model. These anomalies are not large. They are at the edge of statistical significance, hints rather than certainties. But they are persistent, appearing in multiple independent measurements from satellites like WMAP and Planck. The most famous is the axis of evil, a provocative name for an unexpected alignment in the temperature fluctuations. The largest scale variations in the cosmic microwave background, the quadrupole and octupole moments, appear to be aligned with each other and with the plane of the solar system. This should not happen. The cosmic microwave background was emitted billions of years before the solar system formed. There is no reason for its structure to align with the geometry of our planetary orbits. The alignment could be a statistical fluke. When you measure many properties, some will appear correlated by chance. But the axis of evil has survived multiple tests. It appears in both the WMAP and Planck data, independent measurements that use different instruments and analysis techniques. The probability that it is random is low, though not low enough to claim a discovery. Another anomaly is the cold spot, a region of the sky where the cosmic microwave background is significantly colder than average. The cold spot is not just a single point, it is a large patch, about 5 degrees across, roughly 10 times the size of the full moon. Statistically, a fluctuation this large should be extremely rare, with a probability of less than 1% in the standard model. Yet there it is, staring back from the southern sky. Some cosmologists have proposed that the cold spot is a supervoid, an enormous region of space with much lower density than average. As light from the cosmic microwave background passes through this void, it loses energy, cooling the radiation. But simulations suggest that even the largest void should not produce a cold spot this pronounced. The anomaly remains unexplained. A third anomaly is the hemispherical asymmetry. The temperature fluctuations in one half of the sky are slightly larger than in the other half. This violates the assumption of isotropy. The universe should not have a preferred direction. Yet the data shows a clear difference between the northern and southern hemispheres of the cosmic microwave background. The asymmetry is subtle, but it is statistically significant. These anomalies could be signs of new physics. They could indicate that the universe is not perfectly isotropic, that space has preferred directions or regions with different properties. They could suggest that cosmic inflation was more complex than the simple models predict, with additional fields or interactions that left imprints on the cosmic microwave background. Or they could point to something even more radical, a breakdown of the cosmological principle on the larger scales. But they could also be nothing. Statistical fluctuations are inevitable when measuring countless properties of a finite dataset. Some correlations will appear by chance. The human mind is wired to find patterns, even in noise. Cosmologists are trained to be skeptical, to demand extraordinary evidence before claiming extraordinary discoveries. The anomalies are interesting, but they are not yet conclusive. Future observations will decide the issue. Upcoming missions will map the cosmic microwave background with even greater precision, testing whether the anomalies strengthen or fade. If they persist, they will demand an explanation. If they vanish, they will become footnotes, cautionary tales about the dangers of overinterpreting data. For now, the universe remains mostly isotropic, mostly uniform, mostly predictable. But the anomalies linger, whispering that something might be wrong. Trillions of years from now, the universe will be unrecognizable. The stars will have burned out, the black holes will have evaporated, the galaxies will have drifted so far apart that observers in the Milky Way will see nothing but darkness. This is the heat death, the slow dimming of the cosmos into a cold, empty, eternal stillness. It is not an explosion. It is not a collapse. It is a fading, a gentle slide into equilibrium where no energy flows, no work is done, and nothing changes. This fate is written in the laws of thermodynamics. The second law states that entropy, the measure of disorder, always increases in a closed system. The universe is the ultimate closed system. It contains all matter, all energy, all information. Over time, energy spreads out. Hot regions cool, cold regions warm, differences in temperature disappear. Eventually, the entire cosmos reaches the same uniform temperature, a state of maximum entropy called thermal equilibrium. But the heat death is not just about temperature. It is about information, structure, and time itself. In a universe at maximum entropy, there are no gradients, no concentrations of energy, no differences that could be exploited to do work. The laws of physics still operate, but nothing happens. The universe becomes a featureless void, a sea of particles moving at random with no net change, no progress, no future. The timeline to heat death is staggering. Today, the universe is 13.8 billion years old. Stars are still forming, Galaxies are still colliding, black holes are still growing. This is the golden age of cosmic history, the era when the universe is most active, most interesting, most alive, but it will not last. In about 1 trillion years, star formation will cease. The last clouds of hydrogen and helium will have collapsed into stars, and those stars will have burned through their fuel. The universe will enter the degenerate era, a time when the only sources of light are fading white dwarfs, dim red dwarfs, and occasional flashes from colliding brown dwarfs. The galaxies will still exist, held together by gravity, but they will be dark. In 10 to the power of 14 years, 100 trillion years, the last stars will burn out. The universe will be filled with stellar remnants, white dwarfs, neutron stars, black holes, and planets drifting through the void. The only light will come from the occasional merger of two dead stars, brief flares of energy quickly absorbed by the darkness. In 10 to the power of 30 years, protons may begin to decay if grand unified theories are correct. Matter itself will start to disintegrate, slowly converting into radiation and lighter particles. The planets, the asteroids, the remnants of civilizations, everything made of atoms will dissolve into a diffuse gas of photons and neutrinos. In 10 to the power of 100 years, black holes will dominate the universe. They are the last structures capable of holding matter together, the final refugees of complexity in an increasingly uniform cosmos. But even black holes do not last forever. Hawking radiation, a quantum effect at the event horizon, causes black holes to evaporate. The larger the black hole, the longer it takes. A black hole the mass of the Sun will evaporate in 10 to the power of 67 years. A supermassive black hole will take 10 to the power of 100 years or more. When the last black hole evaporates, the universe will enter the dark era. Only photons, neutrinos, and a few stray particles will remain, spread across a volume growing ever larger as space continues to expand. The temperature will drop toward absolute zero. No stars, no planets, no black holes, no structure of any kind. Just an endless expanse of empty space, punctuated by the rare flicker of a photon travelling forever through the void. This is the heat death. It is not an end in the sense of a final moment. It is a state, a condition that persists forever. Time continues to pass, but nothing changes. The universe becomes a frozen tableau, a snapshot of maximum entropy that lasts for eternity. There is no reset, no rebirth, no new beginning. The cosmos simply is, unchanging and dark, for all time. But this is only one possible future. If dark energy evolves, if it weakens over time, the universe may not expand forever. Gravity could take over. The cosmos could collapse back on itself in a big crunch. Or if dark energy strengthens, the expansion could accelerate so violently that even atoms are torn apart in a big rip. The fate of the universe depends on the behavior of dark energy, and that remains one of the deepest mysteries in physics. If dark energy strengthens, the universe will not fade quietly. It will be torn apart. This is the big rip, a catastrophic end in which the expansion of space accelerates so violently that even atoms are ripped apart. It is not a collapse. It is not a gentle dimming. It is a violent unraveling of everything that exists, driven by dark energy growing stronger with each passing billion years. The scenario depends on the equation of state of dark energy, a number that describes how the energy density responds to the expansion of the universe. If dark energy behaves like a cosmological constant, its density remains fixed as space expands. The universe will accelerate forever, but the acceleration rate will stay constant. This leads to the heat death, a cold and dark but ultimately gentle fade into equilibrium. But if dark energy is phantom energy, a hypothetical form with an equation of state less than -1, its density increases as the universe expands. The more space there is, the more dark energy appears. The more dark energy there is, the faster space expands. This creates a runaway feedback loop, an acceleration that grows without limit. At first, the effects are subtle. Galaxies that are not gravitationally bound to the Milky Way drift farther away, disappearing beyond the cosmic horizon. The universe appears to shrink, growing emptier and darker as more structures vanish from view. This is the same fate predicted by the heat death scenario, but the big rip does not stop there. As dark energy strengthens, the expansion accelerates. Eventually, the repulsive force becomes strong enough to overcome gravity on larger and larger scales. Galaxy clusters begin to dissolve. The gravitational bonds holding them together are not strong enough to resist the expanding space. Individual galaxies drift apart, isolated in a cosmos that is growing faster than light can cross it. The timeline depends on how quickly dark energy strengthens. In some models, galaxy clusters dissolve about 60 million years before the final rip. The Milky Way itself, held together by the mutual gravitational attraction of hundreds of billions of stars, begins to feel the strain. Stars on the outer edges are pulled away, stripped from the galaxy by the accelerating expansion. About 3 months before the end, individual solar systems disintegrate. The gravitational bond between the Sun and the Earth, strong enough to have lasted for billions of years, is overpowered by the expansion of space. Planets are flung into the void, orbiting nothing, drifting alone through a cosmos that is tearing itself apart. 30 minutes before the rip, the Earth itself disintegrates. The electromagnetic forces holding molecules together are overwhelmed. Mountains crumble, oceans evaporate. The planet fractures into countless pieces, each fragment pulled apart by the relentless expansion of space. Any remnants of life, if they still exist, are obliterated. In the final fraction of a second, atoms themselves are ripped apart. The strong nuclear force, the most powerful force in nature, is not strong enough. Protons and neutrons dissolve into quarks. Then even the quarks are torn apart. Space expands so rapidly that particles separated by the diameter of an atomic nucleus can no longer interact. The fabric of reality unravels into a sea of isolated fundamental particles, each one alone in an infinite void. The Big Rip ends in a singularity, a moment when the expansion rate becomes infinite. The Hubble constant, which measures how fast space is growing, diverges. The scale factor of the universe becomes infinite. Space itself ceases to have meaning. Time, distance, causality all break down. The universe does not fade, it ruptures. Current observations suggest the Big Rip is unlikely. Measurements of dark energy indicate that its equation of state is close to -1, consistent with a cosmological constant. If dark energy remains constant, the universe will expand forever, but the expansion will not accelerate without limit. The heat death, not the Big Rip, is the most probable fate. But the data are not conclusive. Dark energy could be evolving. If it is phantom energy, if its density is increasing over time, the Big Rip becomes inevitable. Some estimates suggest the rip could occur in as little as 22 billion years, less than twice the current age of the universe. Others place it trillions of years in the future. The timeline depends on how dark energy behaves, and that remains one of the deepest mysteries in physics. The Big Rip is the universe at its most violent. It is not the gentle dimming of the heat death, nor the symmetric collapse of the Big Crunch. It is the cosmos tearing itself apart, driven by an invisible force that grows stronger every moment, until nothing remains but isolated particles drifting through an infinite void. Is our expanding universe one bubble in an infinite foam? This is the multiverse hypothesis, the idea that the cosmos we observe is not the totality of existence, but a single region within a vastly larger structure. Beyond our observable universe, separated by vast expanses of inflating space, other universes may exist, billions of them, perhaps infinite, each with different physical laws, different constants, different histories. The idea arises from cosmic inflation, the theory that the universe underwent a period of rapid expansion in its first fraction of a second. In most models of inflation, the process does not happen everywhere at once. It begins in a small region of space, driven by a field called the inflaton. That region expands wildly, becoming the observable universe. But outside that region, space continues to inflate, and in some places, inflation ends, creating new bubble universes. This process repeats forever, producing an infinite number of disconnected regions, each one isolated from the others. This is eternal inflation, a scenario in which some regions of space are always inflating, always creating new bubbles. The multiverse is not a collection of universes floating in space. It is a branching structure, a fractal of inflating regions and stable bubbles. Most of the multiverse is dominated by inflation, expanding faster than light, forever generating new pockets where inflation ends and matter forms. Each bubble universe is causally disconnected from the others. The space between them is expanding so rapidly that no signal, no light, no information can ever cross the boundary. An observer in one bubble cannot see, measure, or interact with another bubble. The other universes are not hidden, they are inaccessible, forever beyond the horizon. But the most radical implication of the multiverse is not that other universes exist. It is that they may have different physical laws. In string theory, a leading candidate for a unified theory of physics, the constants of nature are not fixed. They depend on the configuration of extra dimensions, the shape of the hidden geometry that underpins reality. Different configurations produce different constants, different masses for particles, different strengths for forces, different values for the cosmological constant. This leads to the landscape problem. String theory predicts something like 10 to the power of 500 possible configurations, each one corresponding to a different set of physical laws. Most of these configurations would produce universes hostile to life. Stars would not form, atoms would not bind, chemistry would be impossible. But in an infinite multiverse, every configuration is realized somewhere, and we inhabit one of the rare bubbles where the constants allow for structure, complexity, and observers. This is the anthropic explanation for fine-tuning. The cosmological constant, the mass of the electron, the strength of gravity, all appear to be finely tuned for life. If any of these constants were even slightly different, the universe would be sterile. The multiverse offers a solution. The constants are not tuned by design. They are random. But in an infinite multiverse, every combination exists somewhere. We observe the constants we do because we could not exist in a universe where they were different. Critics argue that the multiverse is not science. It makes no testable predictions. Other universes are by definition unobservable. If a theory cannot be tested, cannot be falsified, it is not physics, it is philosophy. The multiverse, they say, is an intellectual surrender, a retreat from the goal of explaining why the universe has the properties it does. Proponents counter that the multiverse is a natural consequence of inflation, one of the most successful theories in cosmology. It is not ad hoc. It emerges from the mathematics. And while other universes cannot be directly observed, the theory makes indirect predictions. The statistical distribution of constants in our universe should match what we would expect if we were randomly selected from the ensemble of all possible bubbles. Some have argued that observed anomalies in the cosmic microwave background, subtle deviations from perfect uniformity, could be the result of collisions with other bubbles in the early universe. The multiverse is either the ultimate answer or the ultimate cop-out. It explains everything by explaining nothing. It resolves fine-tuning by making fine-tuning inevitable. It turns the question of why the universe has the properties it does into a question of probability and selection, and it leaves us with a cosmos far larger, far stranger, and far lonelier than we ever imagined. Our observable universe, everything we can see or measure, may be a single bubble adrift in an infinite ocean of other realities. The universe is not expanding into anything, but that does not make the question go away. For as long as humans have studied the cosmos, we have asked, what lies beyond? What is the universe contained within? What surrounds it? The question is hardwired into the human mind, a consequence of living in a world of edges and boundaries. Every object we encounter has an inside and an outside. Every room has walls. Every planet has a surface. We cannot help but project that structure onto the universe itself. But the universe refuses to cooperate. General relativity describes space not as a container, but as a dynamic fabric that bends, stretches, and evolves. Space is not something that exists inside something else. It is the framework within which existence unfolds. When cosmologists say the universe is expanding, they mean the metric of space-time is changing. Distance is not a fixed property. It is a relationship, and that relationship is growing. The question, what is the universe expanding into, assumes there is some pre-existing void, some larger arena into which the cosmos is growing. But this is a category error, a confusion of language that arises because we lack words for what the universe truly is. The cosmos is not embedded in anything. It is not surrounded by anything. It is the totality of space, time, and existence. There is no outside. But the human mind struggles with this. We picture the universe as a balloon inflating, pushing into empty space. We imagine a boundary, a place where the universe ends and something else begins. But there is no boundary, no edge, no wall marking the limits of existence. If you could somehow travel faster than the expansion of space, you would not encounter a barrier. You would simply find more space, more galaxies, more structure extending as far as you could travel. Some cosmologists have proposed that the universe is finite but unbounded, like the surface of a sphere. An ant crawling on a sphere can travel in any direction forever without reaching an edge, yet the surface is not infinite. It has a finite area. The universe could work the same way, with space curving back on itself in dimensions we cannot visualize. You could travel in a straight line for trillions of years and eventually return to where you started, never encountering a boundary. But observations suggest the universe is flat, or very close to it. The cosmic microwave background, mapped by satellites like WMAP and Planck, shows temperature fluctuations that match the predictions of a flat geometry to extraordinary precision. If the universe has curvature, it is so small that it could not be detected even with the most sensitive instruments. A flat universe extends infinitely in all directions. There is no edge, no center, no special location. The question also assumes that expansion requires space to expand into, but this is not how relativity works. Expansion is not objects moving through a fixed background. It is the background itself changing. The metric, the ruler that measures distance, is stretching. A galaxy 1 billion light-years away today will be farther tomorrow, not because it moved, but because the space between here and there multiplied. The universe does not need a container. It is not pushing into anything, it is simply becoming more. Yet the question persists. It haunts cosmology, philosophy, and the human imagination. What is outside the universe? The only honest answer is that the question is meaningless. The universe is not the kind of thing that has an outside. It is not an object in space. It is space. And space is all there is. There is no beyond, no exterior, no surrounding void. The cosmos is self-contained, complete, and sufficient unto itself. But even this answer does not satisfy. It resolves the question by declaring it unanswerable, by defining the universe in such a way that the question cannot be asked. And perhaps that is the deepest lesson. The universe is not obligated to make sense to the human mind. It is not required to fit into categories we understand. It simply is, expanding without an outside, stretching without a container, refusing to give us the comfort of walls. The universe does not expand into anything because there is nothing for it to expand into. This is the answer cosmology gives us, refined over a century of observation, theory, and mathematical precision. Space itself is the thing growing. Distance is not a fixed property. It is a relationship, and that relationship is changing. The fabric of space-time stretches, carrying galaxies apart, multiplying the void between them. There is no stage, no arena, no container. The universe is not an object in space. It is space. The expansion was discovered by Edwin Hubble in 1929, confirmed by decades of observation, explained by Einstein's general relativity, and traced back to the Big Bang 13.8 billion years ago. The cosmic microwave background, the oldest light in the universe, provides direct evidence that the cosmos was once far hotter, denser, and smaller. Cosmic inflation explains how quantum fluctuations were stretched to cosmic scales, seeding the structure we see today. Dark energy, mysterious and unexplained, drives the expansion faster every year. The universe is finite in age but possibly infinite in extent. It is flat or very close to flat, stretching in all directions without boundary or edge. The observable universe, limited by the speed of light and the age of the cosmos, is a sphere 46.5 billion light-years in radius. Beyond that lies more universe, forever hidden, forever unknowable. The ultimate fate of the cosmos depends on dark energy. If it remains constant, the universe will expand forever, accelerating into a cold heat death where stars burn out, black holes evaporate, and entropy reaches its maximum. If dark energy weakens, the expansion could stop, and gravity could pull everything back into a big crunch. If dark energy strengthens, the cosmos could be torn apart in a big rip, with even atoms disintegrating in the final moments. Recent observations suggest dark energy may be evolving, weakening over time. If confirmed, This would rewrite the future of the universe and challenge the assumption that the cosmological constant is truly constant. The next few years of data from telescopes like the James Webb Space Telescope and the Dark Energy Spectroscopic Instrument will determine whether the cosmos is destined for heat death, collapse, or something entirely unexpected. But none of this answers the deeper question. Why does the universe exist at all? Why does it have the properties it does? Why is space expanding rather than static? These are not questions physics can answer. They lie at the boundary of science and philosophy, where observation gives way to speculation and wonder. The universe does not expand into anything. It expands as everything. Space is not a container. It is the totality of existence, the only arena where events can unfold. There is no beyond, no exterior, no surrounding void. The cosmos is self-contained, complete, and sufficient unto itself. It refuses to give us the comfort of walls, the reassurance of edges. It simply is, stretching without an outside, growing without a container, existing without explanation. And perhaps that is the deepest truth. The universe does not owe us an answer. It is not obligated to make sense. It is not required to fit into the categories we understand. We are fortunate to live in an era when the evidence for the Big Bang is still visible, when the cosmic microwave background still glows, when the expansion of space can still be measured. Billions of years from now, that evidence will fade. Future civilizations, if they arise, will inherit a universe that appears static and almost empty, with no way to discover the history we have uncovered. We are living in the golden age of cosmology, the brief window when the universe reveals its secrets. The expansion is the proof. The cosmic microwave background is the witness. Dark energy is the mystery. And the question of what the universe is expanding into is the reminder that reality does not bend to human intuition. It simply is, vast and strange and utterly indifferent to our need for answers. The universe is expanding, that much is certain, but nearly everything else is uncertain. We do not know what dark energy is. We do not know why the cosmological constant has the value it does. We do not know whether dark energy is constant or revolving. We do not know if the universe will expand forever or collapse back on itself. We do not know if space is infinite or finite. We do not know what came before the Big Bang, or if the question even makes sense. We do not know whether other universes exist, whether the multiverse is real, or whether the constants of nature could have been different. Recent observations have shaken the foundations of cosmology. In November 2025, a new study suggested that the universe's expansion may already be slowing down, not speeding up as previously thought. The research, led by Young-Wook Lee at Yonsei University in South Korea, analysed corrected supernova data combined with baryon acoustic oscillations and cosmic microwave background measurements. The findings, published in the monthly notices of the Royal Astronomical Society, indicate that dark energy is weakening over time and that the cosmos has already entered a phase of decelerated expansion. If confirmed, this would mark a paradigm shift. For nearly 3 decades, astronomers have believed the universe is accelerating toward an endless expansion. But the new data suggests otherwise. The universe may reach a maximum size in about 11 billion years, then begin to contract. In another 8 billion years, it could collapse back into a singularity and a big crunch. The total lifespan of the universe from Big Bang to Big Crunch would be just 33 billion years. But the findings are not yet conclusive. Other researchers urge caution, noting that the data are complex and the analysis is still being debated. The Dark Energy Spectroscopic Instrument, which has observed 15 million galaxies and quasars in its first 3 years, continues to provide hints that dark energy may evolve with time. But the error bars are large. The statistical significance is strong but not overwhelming. Future observations from the Vera C. Rubin Observatory and other telescopes will determine whether the universe is truly slowing down or whether the data are misleading. The Hubble tension remains unresolved. Measurements of the expansion rate from the local universe give a value of about 73 kilometers per second per megaparsec. Measurements from the early universe, based on the cosmic microwave background, give a value of about 67. The discrepancy is statistically significant and has grown stronger with more precise data. Either one of the measurements is wrong, or the standard model of cosmology is incomplete. The nature of the cosmic microwave background anomalies remains unexplained. The axis of evil, the cold spot, the hemispherical asymmetry, all of these deviations from perfect isotropy persist in the data. They could be signs of new physics, hints that the universe is not perfectly uniform. Or they could be statistical flukes, patterns that will vanish with more observations. The flatness of the universe is extraordinary. Observation suggests space is flat to within a fraction of a percent. But why? Inflation explains how initial curvature was smoothed out, but it does not explain why the universe should be flat today. The density of matter and energy must be tuned to the critical value with astonishing precision. This is the flatness problem, and it remains unsolved. The multiverse hypothesis remains untestable. If eternal inflation is correct, our observable universe is one bubble in an infinite foam of other universes. But those other universes are, by definition, beyond the horizon. They cannot be observed, measured, or interacted with. The multiverse explains fine-tuning by making every configuration inevitable, but it does so at the cost of making no testable predictions. Is it science or philosophy? The debate continues. The ultimate fate of the universe is uncertain. If dark energy remains constant, the cosmos will expand forever, cooling into a heat death. If dark energy weakens, the universe will collapse in a big crunch. If dark energy strengthens, the cosmos will be torn apart in a big rip. Each scenario leads to a different end, and which one is correct depends on the behavior of dark energy, which remains the deepest mystery in cosmology. We are living in the golden age of cosmology, the brief window when the evidence for the Big Bang is still visible and the expansion of space can still be measured. But we are also living in an age of profound uncertainty. The universe is revealing its secrets, but it is also revealing how much we do not know. The expansion is real. The rest is still being written.